You have this immersion, maybe. Or maybe time. 我试一下。哦。Oh, no. No, no, no. Maybe just standard. Okay. Okay. I think we can begin now. So hello everybody. Welcome to our tutorial from the multimodal large language model to human level AI. It's very honorable to host the tutorial today. So okay. So in today's tutorial, we'll talk about in the following aspects, like the modality, the instruction tuning, the reasoning efficiency, and beyond. So first about Fei Hao will give an introduction to our tutorial, and in the following tutorials, and so other speakers will give more information. Okay, so let's begin. So hi Hao, you can start now.
Okay. Oh, okay. Thanks. So hi everybody. So it's more than exciting for us to give this tutorial series about the multimodal LLM from MLM to human language AI. So thank you everybody for your attention. So we are a team from National University of Singapore, University of Wisconsin Madison, and the University of Maryland, and Shanghai Jiao University, and the Nanyang Technology University, and the Skywork AI. So all of us are closely working on the multimodal LLMs and the relevant topics. First, let me give a brief introduction to this grand topic of MLM. So, okay, my name is Hao, a research fellow at NUS. Yeah, let's start from the magic scaling law. So in the field of AI, over the past 2 decades, researchers have discovered that when dramatically increasing model parameters and data, remarkable phenomena occur. So large models lead directly to emergent behavior. So as we can see here, under the scaling law, we have fully entered the era of LLMs in the last 3 years. So with the emergence of LLMs, today's most advanced purely language-based LLMs like ChatGPT have nearly approached the human-level AI. I mean, the human-level intelligence. For example, current LLMs have an unprecedented capability for very deep semantic understanding of language. Here I just showcased an example, and also the incredible numeric analysis capability, also the amazing mathematic reasoning ability. And there is a crazy trend in the research community about LLMs just last 1 year. So research on LLMs is progressively rapidly, and new iterations of various LLMs are emerging at a very fast speed. Now let's go back from language-oriented LLMs to the multimodality. Okay, we all understand that language is only one part of the sensory world we live in. So we consistently perceive information through various modalities like vision, sound, vision, sound, 3D, depth, touch, taste, and smell, etc. Not just language only, right? So in practice, there are many applications requiring the multimodal data, such as the autonomous driving, medical diagnosis systems, and smart home assistants. So this prompts the research community to think one important question: can we transfer the success of LLMs to multimodal LLMs, enabling to comprehend the multimodal information as deeply as they understand the language, right? So achieving true AGI would undoubtedly require the ability to perceive and interact with the world through various modalities, pretty much like we human do. So unfortunately, the MLM community has gained significant traction over the past 1 or 2 years, and it is now developing so rapidly. Yeah, you just feel it from this roadmap. A lot of MLMs are just invented every month. And another roadmap. Okay, so this tutorial is dedicated to giving a thorough tour to MLM topic. So in what follows, we try to answer first, what we have achieved about MLMs. We will walk through the key technical aspects around the MLMs and give detailed taxonomy of existing research. And second, where to go next of each aspect. So we will provide insights and describe the open challenges and then spark the future directions. We believe there are some key aspects for building more powerful and capable MLMs. So, for example, the first, the architecture, and also the multimodality of MLMs, and also the instruction tuning, and also the human level multimodal reasoning, also the hallucination issues, right? And of course, we also focus on the efficient construction of MLMs. So all these parts together can lead to the goal of building stronger MLMs towards human level AI. So for the architecture design part, Yuan Yao will give the tutorial. What is the current popular architecture of MLMs? For the modality and the functionality part, I will give the tutorial. Yeah. And Haotian Liu will present us the content about MLM instruction tuning. Then Fu Xiaoliu will introduce everything about the multimodal hallucination. Zhuo Shenzhang will elaborate on the multimodal reasoning with MLMs. And Ao Zhang will introduce MLM efficiency, like what is the most efficient MLM architecture to achieve high performance. And finally, everybody will sit around together and discuss more about how to go from here, MLM, to the final goal, human level AI. And also Prof. Yan Shuichen and Han Wangzhang will join the discussion. So our tutorial will start from now to 6 p.m. Each session will take like 30 minutes. In the middle of the tutorial, we will have 1 hour for coffee break. Okay, so you can raise questions during the tutorial or just join our Google group for discussions. And we will release all the materials like slides and the video records at the homepage afterwards. And I think now let's move on. Hi. Oh, thank you. You can host everything. Yeah, I think
hello.
Yeah.
So maybe it's time for Elliot, right?
Okay. So, hello everyone. I'm Yuan Yao. So I'm a research fellow from the National University of Singapore, and the next I will go through the architecture about multimodal LLMs. So this is the overview of this lecture, and first we'll talk about the basic architecture. There are different ways to achieve a multimodal LLM nowadays, basically two ways, and the discrete ways and a continuous way. And for multimodal perception, there are various ways for multimodal encoding. And then we'll talk about how to project these multimodal signals into the large language models. And for the backbone LLMs, so currently the conclusions are very we have agreement on the backbone LLMs, so there are no specific limitations for the backbones. So if you have bigger and stronger backbone LLMs, you will get good performance. So this will not be the main focus of this for this tutorial. So we will focus on other multimodal architectures. So for the decoding side projection, we'll talk about how to let the representations from LLMs to decode into other modality information. And finally, we'll talk about how can we present these semantics in specific multimodal information signals.
Hi, Yuan. You don't open your camera. I think you can open your camera.
Okay. So I think the bandwidth is limited, so this can gives you better, more fluent video presentations about slides. Okay. So this is about our basic architecture, and so let's go first to an overview of the current multimodal LLM architecture. So the primary idea of current multimodal LLMs is we build the multimodal capability based on the intelligence of a strong language intelligence. So the premises is that there are very strong emergent capabilities observed in the language-based LLMs, and these large language models have generally possessed very powerful semantic understanding capabilities, and also for reasoning and the interaction. And so a language is a very special modality in addition to other commonly observed modalities. So it is a good modality for carrying intelligence. This is maybe partially because we humans, we summarize high-level semantics into languages, and it is also very natural for humans to interact to other modalities through language. So this is the basic foundation of multimodal large language model. So given this phenomenon, so nearly all the current multimodal large language models, they are built based on a strong language-based LLMs. So the LLMs will act as a core decision-making model, or the central brain of a representation processor. So the basic paradigm is that we extend the capability boundary of a text-only language model to many other modalities, including the encoding and the decoding. So this is achieved by adding some external non-textual modality modules, like the modality encoder or decoder, to the large language model. And so this is important because in one way we extend the capability boundary, and we believe, and the researchers will believe this is the next important milestone towards more advanced intelligence, because we are not only limited into one textual modality, and also this will also give us more applications to deal with many tasks that require us to deal with more modalities. Okay, so this is the basic idea. And given this idea, there are basically two mainstream ways to achieve this. So the first one is the discrete, to let the LLM to act as a discrete scheduler and the controller. So this is very popular in the early stage of multimodal LLMs. So here the role of an LLM is to receive the textual signals and to instruct textual commands to function call some downstream modules and like some external tools. So the key, so this is the basic architecture, and the user will act with the LLMs, and the LLMs will schedule a textual command to some downstream module like the Stable Diffusion or other tools, and this information are passed together through some pure text commands. Okay, so in the early stage, many multimodal LLMs will act in this way, like the visual ChatGPT and Hugging GPT. So these are very famous models. So let me give you some example. Maybe you will query about a model, and to better understand it, you will call, so the ChatGPT will call some external tools like Leap, and if you want to express some information in other modalities, maybe you will call the Stable Diffusion to visualize these matrix into other modalities. And this is also true for Hugging GPT. So a central LLM will manage other manage other tools in other modalities through the textual-based commands. And so the advantage of this system is it is quick to build. So you can essentially build it without training. You just need a ChatGPT and many existing tools, and it is very flexible to extend this system to many other tool features. For example, if you want to generate the audio, you can just include an audio tool into this tool base. And but the disadvantage is that there will be significant information loss in the text medium, because a central LLM can only communicate with other tools through a text, and this will be the bottleneck of the multimodal information flow. So so currently the dominant way to achieve a multimodal LLM is to let the LLM to act as a joint part of the system. So here the role of the large language model is to perceive the multimodal information and react by itself. So it is basically in a structure of encoder. So the multimodal information will be first encoded and into continuous representations and passed into the large language models, and then decode into the text and other modalities. So the key feature here is that the LLM is the key joint part of the system, and the information of different modalities are passed in a continuous way without too much information loss. And actually, this is the dominant way of current multimodal large language models. I think over 90% of the works nowadays belong to this category, and it gives us higher upper bound capability, and also the different capabilities and information are better integrated into a unified model. So it is considered to be a more promising way. So so next we will go through into the different parts about how to design or implement such a multimodal large language model. So so this we have many modalities, but since our time is limited, this lecture will basically focus on the visual on the vision or the image modality and the text modality. So that will be our basic focus of this lecture, but we can easily extend this paradigm to other modalities. So for the visual encoder, and Clip VIT is the most popular choice for implementing the vision language models. So the advantage of CLIP VIT, many works have verified this advantage. And I think the main reason, there are two important advantage of a CLIP VIT. The first is that it can provide good image representations that is well aligned with text space. So you can train with very efficiently to align them together with a large language model to achieve good image understanding performance. And secondly, a very good property is that the CLIP VIT is scale very well with respect to parameters and the data. So look at this figure. If you train larger CLIP VIT in larger parameters, the zero-shot performance consistently grows. So this is also a very active field. Training larger VITs will bring better representations in semantics to serve the multimodal large language model. And also SCLIP is recently gaining much increasing popularity since it can achieve relatively good performance and in a smaller size. So this can be trained more efficiently. So in fact, we have many ways to choose a visual encoder. We will not go into too much details. I think an important topic nowadays is the high resolution of multimodal large language models. We have been aware that the high resolution perception is very important. That is because the limitations of existing pre-trained VITs, there is an important limitation in common. So they are pre-trained in a fixed low resolution. This is typically 200 by 200, or also in a square shape, in a fixed square shape. And and in fact, high resolution perception is essential. If you inherit this low resolution in the downstream multimodal large language model training, the capability will be greatly limited. So this is especially important for OCR capability. If you want to recognize the fine-grained visual details in this image, you will need high resolutions, and the low resolution encoding will miss important fine-grained visual details. So to achieve this, so there are, in fact, this is also a very hot topic and active area. So there are many ways to achieve this. The most popular way to achieve a high resolution multimodal large language model is an image slice-based method. So this is a picture from the LavaNext. The basic idea is to split the high resolution image into several lower resolution slices. So each slice will be more similar to what is pre-trained for VIT. So this will not involve many OOD problems. And also this overall image is also resized into a lower resolution to give an overview of this image. And then these features will be concatenated together into the large language models. And I think the mainstream model nowadays will commonly use this paradigm, such as GPT-4V. You can infer from their API policies to get this, and also famous models like LavaNext and other models. And a very important conclusion about high resolution multimodal large language models is that if you can enable the model to perceive high resolution images, you can get significantly better OCR capabilities even without adding new data. So consider this, you build a model based on Lava 1.5, and if you enable the model to perceive like 6 times more pixels to an image, and even without adding new data, the text VQA will get a significantly better result. So, and another very important direction of high resolution encoding is the dual branch encoders. So the basic idea is that you can use a larger VIT to process the image in a lower resolution to get better semantics and knowledge from this low resolution representations, since you can use a larger VIT. and to process it into a high resolution, you will need a smaller VIT, and then you can process it in a high resolution. And how to integrate these two representations together? So maybe you can use this coarse-grained overall information as a query to gather some information from the high resolution representations using like cross attention to achieve this. So basically, there are two complementary branches to encode the different views of imaging to images, and then you will get good results for semantics and resolution. So there are also many good works use this solution as well. And also there is also another solution is VIT free. This is less used, but also an important idea to achieve this. So the basic idea is that we do not need VIT since it gives us many limitations and also in scaling to larger models. So maybe we can get rid of the VITs and just linear project the pixel patches into tokens using a very simple linear projection. And then these image tokens and the text tokens are jointly modeled by a large language model or a joint model. So representative models, so like Fuyu and Alter HD. So this is potential. So basically, you will learn the VIT into a single joint parameters of a central model. So the potential good aspect of this solution is that it is a potentially unified way for multimodal LLMs. So you will get rid of the VITs. But currently, we will observe that it will be more costly to train because the VIT will be integrated into the parameters of an LLM, and also this solution will produce lengthy visual tokens because every patches will yield a new visual token, and for other solutions, you will summarize these tokens into fewer token lengths. And also for other for other modalities like audio and 3D point, you will have specific encoders. So we will not talk too much into these details. And also, in addition to design specific encoders for each modalities and connect them to the together. So there are also some works to building a unified multimodal encoder. That is, we can encode different modalities into a joint space. And so ImageBind is a famous work. It embeds all the modalities into a joint representation of image. So there are pairs. So there are modality and image pairs together on the internet, and you can learn them, align them together through contrastive learning. So so the representations from different modalities are well aligned into a joint space of image, and these aligned modality representations can benefit large language model understanding in the multimodal.
Hello. Yeah. Are you speaking?
Yeah. Yes.
Hello.
Hello. Can you hear me? Hi. Al, can you hear me?
Yeah.
Yes, I can hear you. I can hear you.
Yeah, we can hear you.
Okay. Yeah.
Okay, sorry.
Okay. So the language bind also follows a similar paradigm. So you combine different modalities through a language bind. And also this is also for the tokenized, also in addition to the continuous way, you can also represent different modalities into discrete tokens, like in a codebook. So this is the work from NAGPT. So you can tokenize different modalities like speech, text, image, and music into a codebook and let the large language model to process that. And the good way of such paradigm is that you can support unified modeling including the understanding and the generation in an autoregressive next token prediction framework. and it is more commonly used in the image synthesis, like some famous works. So in addition to this, you can also how to connect multimodal information to large language models. So there are various ways like Q-former, linear projection, MLP, and the perceiver sampler, and the C abstractor. So many different choices. And about these different ways, in fact, we have different papers will have different conclusions. So basically, I will select only some conclusions from these works. So two-layer MLP is better than one. So this is from the Lava 1.5. And also in other works, many researchers found that resampler is comparable to C abstractor and MLP. And an important agreement will be that the number of visual tokens, it actually matters, especially for the efficiency. So the resampler and the Q-former and the C abstractor, they typically yield less visual tokens than MLP and the linear, and this will gives you better efficiency in achieving high resolution image understanding. So if you have fewer tokens, the process will be much more efficient. And the next question will be how can we decode the semantics from the large language models to other modalities? So to connect this information, there will be several ways. The first will also be through the text tokens and using pure text commands to pass it to other tools. So this will also be very flexible, but also prone to some information loss. And the second way, it will be the continuous embedding. So in this way, the information loss will be avoided, but you will need a joint training of these models. And the final way will be using some code books. So tokenize different modalities into discrete tokens to perform the modality generation. And for the specific modality generation, so text generation is very natural for large language models. It can achieve good performance in that. And for the for other modalities like visual generation and audio generation, so existing works typically bridge some external modality generation tools to the large language models. Like you can use image diffusion or video diffusion and speech and audio diffusion to achieve that. And also it is also applicable to use some code-based models like VQ-VAE and VQ-GAN-based models to generate other modalities. And so that's the basic idea of the architecture about large language models. And so I think there are also two important topics in architecture that worth mentioning. The first is the multilingual multimodal capabilities. So currently, most multimodal large language models, they are strong in English, but weak in other languages. And we want our model to serve more languages because we have many languages in the world and many communities to serve. And so there are many advantages of building an inherent model to master many languages and interact us with the multimodal information. So the basic challenge will be the lack of multimodal data in other languages. So this is in fact even for Chinese, which is traditionally considered a rich resource language. And the basic idea to resolve this is through the generalizing the multimodal capabilities to other languages using multilingual large language model as a pivot. So the basic idea is that we can achieve good alignment between different languages in a multilingual large language model here in this way, and we can just extensively train a large language model in English in the image text pairs, and then we can achieve generalization to other non-English languages automatically. So this has been well observed in Chinese. So we can pre-train this model in English image text only data. And we can observe that if you have a good multilingual large language model as the backbone, so this capability can be well generalized to other languages in a foundational capability way. So you can ask the model a question in like German, and it will answer the question correctly in English, but the semantics is correct. So this will show that the foundational capability has been generalized, and we can to switch the target language using a very lightweight SFT process. And so this process to switch this target language. And also this process can generalize to different cultures. You can ask the model to describe an image in traditional Chinese form. So that will beyond the expectation to us. Okay. So this paradigm is in fact a common practice nowadays, like many famous bilingual or multilingual large language models. They have adopted this paradigm to achieve a good multilingual multimodal performance. And also there is also very important trending of on-site multimodal large language models. So this is a summarization of recent multimodal large language models. So so we will observe that good performance, like GPT-4V level performance model, will get smaller in size as the time passes by, and also as the on-site computation stably increases. So we will expect that in the future there are many strong models that can deployed on the on-site devices. So so a smaller model can match the larger models, maybe if well trained, like mini CTM Vision series and DeepSeek Mini Gemini. So they are very good examples for on-site multimodal large language models. So an on-site MLM will give you many advantages, such as it will give you higher efficiency and better accessibility, and also better privacy protection, since you don't need to upload all your using information into the server. And also you can also run without network connection in some application scenarios. So okay, so that's all for my presentation. Thank you.
So thank you everybody. So I have a question. Maybe I need to transfer the question to the online part. So any question? Okay, if there is no question, we can move to the next talk. So hi, 好，maybe you can share your slides and introduce the modality part, right?
Okay, yes. Sure. Let me share my screen. Okay. Does that work? Does that work?
Yeah, it's work. Did that
Okay.
work?
Okay. Thanks all. Thanks everybody. So in this part, I will mainly survey the existing LLMs in terms of their modality and functionality support. Yeah. So let's go quickly go through the content. I'll summarize all the existing LLMs, like categorizing them into perceiving and the generation capabilities. Then I'll further get into the more advanced abilities of LLMs, like more unified LLMs. And finally, I'll slightly highlight some the future directions. Okay, so as I mentioned earlier, there are so many modalities existed in this world we live in. Generally, it's logical to cover as many of them as possible in LLMs. So in current research, the most common modalities included language, vision, audio, and 3D. So within the vision category, this generally means images and videos. Given this point, next I will mainly introduce the MLM on these modalities. Okay, so I just made a summary to all existing LLMs according to their modality support and the ability of only multimodal perceiving or simultaneously multimodal perceiving and generation. Okay, I will introduce each type mentioned here one by one in the following sections, but I think it's necessary to declare a point, due to too big number of MMs, it's not possible here to introduce every single model. So I will outline the main features of each type and then provide a brief introduction to one or two representative MMs in each type. Okay, as the most basic version, also the earliest appearance of MLMs, the models in this category, I mean the image perceiving MLMs, are building on top of language-based by incorporating the comprehension ability of images at the input side. So the basic idea is to integrate a vision encoder onto LLM, following the approach described in the last section introduced by Yuan Yao. So really a lot of MMs emerged in this category around the earlier 2023. Yeah, among all this type of MMs, these four models might be likely the most representative ones, like the Blip 2, Lava, and the Flamingo, Mini GPT-4. Yeah, I think there's one MM in this category that stands out as a particularly different one, Fuyu model. Unlike all other existing image-oriented MMs, Fuyu process image data without a vision encoder, and instead directly inputs image impact patches into the MM for interpretation together with the central MM. So I consider this way to be a very interesting direction for future exploration. All right, next up are MMs that can understand video data. So similarly, they achieve this by incorporating a video encoder to enable MM to comprehend the vision signal. I mean the video signal. Due to the limited space, at least only a few representative video MMs here. Yeah, I've provided the architecture diagram for two video MMs, including the video ChatGPT and the video Lava. So unlike encoding images, encoding videos should pay more attention to modeling the dynamic temporality of video. Okay, please refer to the video MM survey paper for more models and details. For 3D perceiving MMs, the approach is quite similar. They incorporate an external 3D encoder to enable LLM to comprehend 3D or point cloud data. Representative models in this category include the 3D LLM and the point LLM. For audio perceiving MLMs, audio signals can cover various types like general sound, specific speech, or even music. Similarly, by incorporating the corresponding encoder and applying projection, LLMs just can understand the audio signal. Here I've just shown the architecture diagrams for this representative audio MLMs. Okay, without further ado, surely following this paradigm, a wider range of other modalities perception capabilities can be integrated into LLM, resulting in X perceiving MLMs. For example, in the biomedical or healthcare domain, there are numerous models and research works available. Similarly, there are numerous MLMs in various fields such as molecular, chemistry, graph, and many others. Everything you can name it. The discussion above concludes the explorations of MLMs that just support understanding single model scenarios. But researchers in the MLM community have discovered that the just focusing on understanding modalities is far from sufficient. Often, MLMs not only need to understand the input multimodal information, but also to generate information in different modalities. So gradually, MLMs with the multimodal perceiving and the generation capabilities have emerged. Here they are. Yeah. Okay. First of all, for images, there are representative models capable of taking both text and images as input and prehending semantics and generating both text and images. For example, DL combines stable diffusion with the embedding to achieve image generation. MU, of course, MU2 generates a code book through autoregulation followed by image generation. Yeah. So for understanding and generating video, there are these models. For example, the GPT-4 video achieves video generation by directly generating pure text, allowing the LLM to call the various external modules for video generation. But the video points, on the other hand, utilize autoregressive generation approach, which leverage the mega-VIT decoder to directly generate videos. Okay, so there's a very similar story for the audio modality operation. For example, SpeechGPT uses the audio decoder and outputs audio content in an autoregressive manner. Actually, there is it is insufficient to consider supporting for only one modality, whether it's understanding or understanding plus generation. So yes, here text is a modality. Text is here is a modality inherent to LM, so we don't count it. Yeah. So in realistic scenarios, modalities often have strong interconnections simultaneously. For example, images and video often co-occur, right? And often videos contain audio signals, right? Also, there is a need to consider any-to-any modality interactions. Yeah, so it is often necessary for MLMs to handle multiple non-textual modalities at once, rather than just one signal modality. First, let's check the combination of text plus image plus video. There are several MLMs that simultaneously support these three modalities. Here, we showcase the ChatUni model. So the implementation approach is quite simple, just adding more corresponding modality encoders or the decoders to the LM. And for the combination of text plus image plus video plus audio, the approach is pretty much similar, but there are more LMs in this category. And for example, the Macau LM, it just integrates the image, audio, and video encoders, and then do the alignment before feeding into LM. Of course, there are so many other ways to achieve this goal. So indeed, integrating a limitless number of modalities is practically endless, right? So some research directly focus on constructing any-to-any MLMs. So this category is closest to the paradigm of AGI, the concept of AGI. So NextGPT is a very pioneering work in this category, introducing the concept of any-to-any MLM for the first time. So this architecture achieves a powerful functionality, and it also is a parameter efficient alignment learning strategy, also demonstrate the novelty. So here is a demo video that showcases any-to-any capability. Let's stay for just like 5 seconds here. Yeah. Okay. Okay. So after expanding support for modalities, researchers in the community began considering how to enhance the depth of MMM capability. So this can be described as achieving the fine-grained capability of MMMs. Currently, this idea has only been implemented in vision MMMs. When considering vision data, previous work focused solely on the instance level overall understanding, but this often leads to inaccurate vision understanding, then even multimodal hallucination issues. So to address this problem, it's necessary to equip MMMs with the pixel-wise visual perception. Such fine-grained capability can be reflected in many tasks, such as the vision grounding, segmentation, editing, and enhancing. Yeah. So currently, based on the support for images and video modalities, this can be divided into two categories. So let me walk you through these MMMs. Surely there are already many pixel-wise MM for images. Generally, users input an image, potentially specifying a region, and the M outputs content based on its understanding, grounding the region content to the specific pixel level regions of the images. They are here. Yeah. Okay. Here I'll showcase the next chat and the Gamma models here. Yeah. And further, we can continue to categorize these MMs based on different perspectives. First, considering the pixel level awareness, whether at the input side or the output side, we can classify them as follows. For example, some models only support the fine-grained pixel awareness at the output side, but some can provide a fine-grained perception in an output result, and also accept the fine-grained input from the user at the input side, right? Okay, let's move on. Based on the granularity of pixels, we can further clarify them as whether supporting bounding box coordinates or directly utilizing the fine-grained mask level segments. And finally, I mean the third category, we can classify them based on whether they support user input interactions. For example, some models cannot support image user interaction, but some can support users specifying a region through inputting the bounding box coordinates. And also some, the most ideal type is to directly support users inputting sketches or doodles freely. Okay, for the pixel-wise MMs for video, there are existing models, of course. So for example, the PG Video Lava can output dynamic grounding segmentation for objects within a video with, while understanding the video. And also Motion Epic achieves fine-grained video on grounding by integrating the video scene graph representations. So it seems like everything is still fragmented. I mean, with various different levels and the granularity of support, as well as support for different modalities. So can we unify all of them? Okay. Okay. So the vision answer this question. Okay. First of all, we can observe that existing MMS for vision tasks suffers from, the uneven coverage of various fine-grained vision task clusters. Also, they cannot simultaneously support both the image and video to pattern homogeneous vision modalities, right? So the emergence of vision model address all these issues. The vision represents the first unified pixel level vision and yeah. So it consolidates tasks such as the understanding, generation, segmentation, and the editing in the vision domain. It lays the foundation for the ultimate form of the next generation of universal vision generalist. Yeah, it's here. Okay. So the model architecture is like this. Please refer to the paper and projects for more information. Here are some demonstrations of the various functions that vision can support. Okay, let's give it a few more seconds. Okay, let's move on. So, what's next? What's next in terms of the MLM modality and the functionality? Here, I'd like to share some, very straightforward directions I consider very important as future work. So first of all, we haven't fully explored the modalities at both the breadth and the depth perspective of task support. So at the modality perspective, most current LLMs focus on integrating the vision modalities such as image and videos, with some also considering the audio, of course. But other many modalities should be included, right? As we human perception of the world covers a vast array of modalities. Even the currently the NextGPT only support full modality. The current version. So there are still quite a good number of modalities to go, such as code, 3D, document, touch, smell, etc. You name it. Also at the task perspective, we should go deeper. Current MLMs for task support, varies. For example, the vision-based MLMs vision has focused on the unifying vision and the image and the video processing under the scope of a pixel-wise tasks. It's a good work though. The next step could further expand the MLMs in supporting the task at a deeper level. Yeah. Okay. So the second angle is quite more concrete about how to achieve a stronger multimodal generation capability. So right now, MLM research is rapidly evolving from the multimodal comprehension only to the multimodal generation. But the current capability for multimodal generation still requires further enhancement compared to the multimodal understanding. So one specific challenge lies in achieving more elegant end-to-end method for modality to modality conversion. For example, NextGPT use software embeddings to connect the backbone diffusion models to generate as many modalities as possible. But actually, this type of method does not support completely the end-to-end training. So a better approach could be, based on the multimodal tokenization technique, transitioning to an autoregressive generation approach. So here is a takeaway of a hot trend in this topic currently is about achieving better video generation, maybe the joint image and video generation through a more robust video tokenization technique, especially when supporting both images and videos. There may be a need to more carefully modeling the spatial aspect of images and the temporal dynamics of videos, right? Okay, so the last angle is about maintaining multimodal multitask synergy. Imagine that we could use LLM as a task dispatcher, right? Combining all existing, the external tool, or say specialists to construct a multimodal agent or generalist, which is capable of supporting various tasks and modalities. But just unifying different tasks does not make a system a strong generalist, because the simple integration of specialists can, but at best only reach the capability of each individual specialist, right? So if so, what is the point? What is the difference from using existing separate specialists? What is the point of the integration, right? So it's all about the generalization ability. Let's think about how to achieve stronger generalization ability. We human don't need to see every case during training, during running, but can do the the analogic reasoning, right? So I'm just wondering, can we achieve that singularity of multimodal GPT points? I mean, the multimodal GPT moments, the real one. I mean, the emergent phenomena by end-to-end training the MLMs with the super large data, the way as in training the language-based LM like GPT. So actually, this is an open question. I think later, shortly, we can have more discussion during the panel session. Yeah. Thanks, everybody. Maybe you may have some question, but we can further we will have a big discussion later. We will address all the questions if you have. Okay, thank you, everybody. So okay, I'll stop sharing.
Okay, so maybe we move the QA part later, right?
Yeah.
Yeah, okay.
Share. Haven't shared. Maybe. I don't have speakers notes, so you can do it whatever you want. Okay. Maybe this one.
No, maybe the next
One. That's the where is cable? Are you seeing the proper screen? Hi, people on the Zoom, are you seeing in the proper slide?
Yes, we can see the slide.
Yeah,
but not in full screen.
Clear?
Yes, clear.
Okay. So there's no point in having this. Yes. But how can I? Okay, yeah. Hello, everyone. I'm Haojian. I recently got my PhD from computer medicine, and I will be presenting overview of multimodal instruction following.
Okay. Haotian, are you sharing the screen in full mode?
So, okay, yeah. I think we need to maybe maybe what we can do is put it here and then I think it's that stuff too. Is the slides correct now?
Yes, it's good now.
Okay. You're not seeing the presenter view, right?
Yes.
Okay, cool. Okay, so this is actually good for me so that I can see the slide a bit. Okay, cool. So yeah, so like let's start with this question. Why do we want to do multimodal instruction tuning? Or why is this process necessary? So there are lots of pre-trained models already, and as already introduced before, like Blip, Flamingo. Those models are vision language models that can understand the visual modalities, and they can perform basic visual reasoning. They can understand what's in the image. But if you give it a very complex question like like what's unusual about the image, or you give it a long context and ask it to reason about it and correlate with the image, it may not necessarily understand this. So the key here is that it does not know that your intent. It may know like very basic intent, like describe something, but it may not know those complex intent. So we need to tune the model to do the instruction following, and instruction following is understanding humans' intent. So another reason why we want to do instruction following is that we want to build a general purpose model where, like, if you have a basic pre-trained model, it has understands lots of things. You may be able to fine-tune it to different tasks. You may be able to fine-tune it to do object detection. You may be able to fine-tune it to segmentation or image capturing, but you may not be able to do it at once. And it may only be able to perform tasks that it has been trained on. For example, like, this is why instruction tuning is not multitask learning. If you just do multitask learning, what you're going to do is that you give an image, give a task token, like this task token 1 means short caption. The task token 2 means yes, no. And you give it some samples and you give it some output and you train a model, it can do all those tasks very well. But when you think like, okay, now I want a long caption, the model, you basically need to create a new task token, but the model knows nothing about those task tokens. So multitask learning is not instruction tuning because it does not automatically generalize to new tasks. And instruction tuning works because it uses natural language task instructions. Its task tokens are natural language, and natural language space is very vast, and it can generalize. So you can train a model on tasks like describe this image in natural text. What's this? Is this something in natural text? And do some task in natural text. And then even if there is some instructions that is not exactly seen during the training, like describe something in detail, it may be able to generalize based on its understanding of the language and its understanding of the visual world. So this is why we want to do instruction tuning and how is it different from those previous paradigms. And this is a basic framework of a multimodal model where you create some instruction following data sets where the instruction following data sets are images, instructions, answers, and you have a basic multimodal architecture. This is an example in Lava 1.5 where you have a vision encoder that can encode an image into visual features. You have a language model that can perform those reasoning and output the text response. And then you also need to have a vision language connector where you can connect the modality between the visual modality and the language modality so that this language model can start to understand those visual semantics. And then, so usually how those training works is that there are two-stage training because before you add those visual encoders, those visual encoders are trained separately from those language models. So you first need to train those connectors so that you train the connector in a way that it can map it into a distribution that our language model can understand. So usually those models will first pre-train this adapter on those data sets like image text pairs data set, so that like it's aligning the different modalities. It allows a language model to understand images, allows the language model to understand videos, understand the audios. And then in the step 2, where as we said, just discussed, like those stage 1 models are just pre-trained models. They understand things, but does not necessarily understand your intent. And then in stage 2, you can fine-tune your language model, or maybe your adapter, or maybe your vision encoder, but you must fine-tune your language model to let it start understand your intent for multimodal tasks. And there are several common training paradigms, like which part you freeze and which part you not freeze, you make it trainable, and you have even more, like you can have like, I don't know, like 9 or even more combinations. So we're not going to discuss all of them, but I'm going to try to provide another perspective of why we're doing this. And this is the first time I'm presenting this in public, so I hope that you can like it. I'm not sure how you will like it. So like I want to discuss this from a perspective on how we created Lava. So when we started to do this, we are asking this question: how can we create such multimodal models that can follow humans' intent? And when we're designing something, it's all about the trade-off. So because like we're at academia and we do not have hundreds of thousands of GPUs, so we need to add a constraint, which is how do we do that efficiently? And I guess this is a constraint that most of those academia labs are going to make. And then let's think what are the things that we want to achieve. First, we want to create a multimodal model. Second, we want our multimodal model to follow human's intent. These are two final capabilities we want the model to have. And then we have two choices. One, we first create we have three choices. We create a multimodal model that follows human intent in one shot, which may consume a lot of resources because now you're trying. Hello?
It does that sometimes. It'll come back in a couple minutes.
Okay, so yeah, so I'll try speak louder, I guess. So like how we are going to create such like basically if we are going to create a multimodal. Oh yeah, hello. Okay, so yeah, if we're creating a multimodal model that can follow human's intent in one shot, then it will take a huge amount of resource because now you're pre-trained from scratch. So we can either choose to first start with a multimodal model, and then we try to make it instruction following, which is we first pre-train on some like basic, like first we do pre-training and then we make them instruction following. Then we probably need a lot of language tokens as well because it's just like multimodal. It's not necessarily like understanding lots of language data. Like it does not know how to code. It does not know about lots of the world knowledge. It only knows a bit of the knowledge that are only associated with the multimodal data, like images. The other way is that we start with a language model which has been trained on trillions of tokens, where it has a great world knowledge, but it knows nothing about the visual world. So it seems like it may be possible that we can make a language model that's already instruction following and make it multimodal. Maybe that will be much easier, but we also need to make a little reasoning as well. So one observation we have is that language model can learn a foreign language efficiently. So the first version of Llama is already trained on English tokens. It's almost only trained on English tokens. But you may be able to let it learn some foreign language with as few as 52K conversations, which is, I guess, maybe less than 1 billion tokens. Like on Hugging Face, you can see those Chinese llama, Japanese llama, Korean llama. Like those language are there are very few tokens of those language in the llama pre-training, but you can train it maybe in an hour on 1A100 or something. So it can learn a foreign language efficiently. So the question is, can we formulate a multimodal learning as a translation problem? Can we translate a multimodal token as a foreign language and translate it into English? So let's say there's a logo of lava, and it's a llama made of lava. And then we think of it as a grid because it is a grid. And let's say it's a 5x5 grid. And then if we think like all the grid are vocabulary, and this is a llama, and also it's somehow lava, and this is like llama, lava, and glasses. This is just glasses. And also like there may be like llama feet, llama tail or something. Let's say we have some text like this, and then we just drop the image completely. And then we let a language model to read this, and then ask question, what's in the image? It may be able to see that it's a llama that's made of lava because like it's very unusual to see llama and lava, where maybe it's brutal that a llama is soaked in lava, which I do not want, I do not like it. And also what's special of this glasses, it can maybe also say something like the llama is wearing the glasses. So if we're able to formulate multimodal learning as a translation problem, then you may be able to think like, okay, we now have already encoder. Then we can just try to train this cross-modal connector to train it as a foreign language translator. And then you can utilize all the knowledge from your language decoder to try to parse this foreign language. So this is great. And we can think of this like the multimodal connector plus the vision encoder as a multimodal tokenizer, which is analogous to language tokenizer, which you tokenize those language words into language embeddings, which have some kind of semantics. And this is, as we just demonstrated. And then, like for those questions, like what's the color of the shirt the man is wearing, like it may already carry something like that, and the model is going to be able to say something like that. So language model can learn a visual foreign language efficiently, but it may still be hard for some of the questions. Now, clever llama, like, can you answer this question? Is a llama facing left or right? It's hard. So it still struggles to follow complex visual instructions. And like question like this, what's unusual about something, or like those spatial related questions, we may still need a bit of tuning, and instead of just solely letting the language model generalize. So that's why we may want to fine-tune the language decoder as well. So that's the reason why we want to design our architecture where we want to first fine-tune the cross-modal connector. Then we also want to, or we need to fine-tune this language encoder if we want to do it efficiently and effectively. And now let's go back, like what do we need now? We need to tune the model for following multimodal instructions. Okay, now let's try to generate some data to generate the multimodal instruction following data. And for pre-training, like we can like source from those large-scale corpus where we have like CC3 millions, those come crawl captions. We have those layout captions where you can use them to, they are paired image text data where images are associated with text so that you can use them to align modalities from visual to text. And those are very quite short, and because they are sourced from English, from the website, so they are quite noisy, but it provides you a large volume of the data that you can train a model for the alignment. There are another kind of the paired image text data, which are more fine-grained, which are those detailed caption data, which are mostly generated by models. And they provide more details about the image. They can provide a higher density of the information because for an image, it may be trying to describe every aspect of the visual content in the image, while the previous image text pairs dataset will only talk about some key components. And it can potentially allow you to align the model much better. And ShareGPTV is an example of such dataset where it tries to recaption the Cocoa captions, where Cocoa caption was originally only 5 sentences, and each of them are also very short. And it can recaption them into a very long caption, and if you pre-train the model on those data, ShareGPT found that it's actually quite helpful for the better alignment. And then the second stage instruction tuning, we're going to fine-tune the language model or adapters, and we want to create such data for that. And there was no like those instruction following data before. One idea is that we can try to use a pipeline called self-instruct. Interesting. Okay, so yeah, what's a pipeline of self-instruct? It's basically trying to let you to create those instruction and instruction following data, where the instruction data are like you have the image, you have the instruction, and you have the answers, and it's quite costly to generate such data solely by human. So approaching language, natural language processing domain was that you can first give the language model such examples like what does instruction following data mean? Like it's actually like instructions, which are tasks, the answers, which are the results of you performing the task, and then you can just use those examples as some demos to demonstrate that to ChatGPT and use it as an example to allow it to generate hundreds of thousands or even millions of such instruction following data, and it can allow you to fine-tune the model to those smaller models. But if we want to apply the same pipeline to multimodal instruction following, you may find that it's quite hard because most of us was doing this research before, I guess, October or September last year, there's no GPT-4V available, so there was no such features. And even after that, you can see that those powerful models still make some mistakes there. And you really want to have your instruction data to be high quality. So what we can do is like, we can try to formulate convert the image into some format that the language model can understand, just like what we did to try to like formulate our image in a grid, but we can formulate in a different way. For example, we can give the model some captions where the caption can describe what's mainly in the image. And also you can give it some bounding boxes where you can provide it like those layouts. When you provide those layouts, like the model can know a bit more about like how those objects are located, and you may be able to answer the question like, is it on the left or is it on the right? Those kind of questions. And this is another work that further dive into this paradigm that formulates like this kind of queries for text-only GPT, where you can tell the GPT model on like what the task is and how you're going to like provide those bounding boxes, how you're going to provide the task instructions, like more fine-grained, like controlling the what kind of the tasks. The original Lava only designs 3 tasks, but this design much more. And also give it some explicit requirements. And then you can like get the outputs from GPT-4, a text-only GPT-4, but the input and outputs are part of the image. So those are the way that you can generate instruction following data about the image in a form of natural conversations, but just from a text-only model. And there are also another source of data which are kind of helpful because we already have a large amount of them. We have VQA, V2, which are those answer questions about the object like properties, details of the visual content, and the answer are usually in a few words. And those provide the visual cues provide those visual cues like in a few few words. And it can be, by training on this, you can train the model for those specific capabilities, and it can be quite helpful. But if you just train the model on those kind of data, it may limit the output length of the multimodal models, because when we train the model, we train it with autoregressive loss, where you let the model to predict something which you tell them as a ground truth. And this may make the model behavior weird. For example, in one of the experiments in Lava 1.5, what we find is that like if you do not, they just train with those natural instructions, and you ask the model a question like, can you tell me what I can cook with these, and you give it an image of the fridge, it will be able to give you a reasonable recipe. But if you train it with those VK questions, which are, you train this with the VK questions together with the instructions, it may got confused because, you know, like this is a can you tell me, like the keyword is can you, and I will tell you like I can, but I won't necessarily tell you like the details. So like this is awkward, and we want to avoid this. So like the most work will converge into a simple solution, which is you give a format prompt which guides clearly on like what it is, and a bit of the information on why this is problematic. So basically, like there are some ambiguous prompts like Q, what's the color, and the answer is and A answer something. And you're training the model with those natural questions, and you're training it to say, wearing a yellow shirt. And usually when you give it a prompt like Q and A, like it will also give some answers similar. But now you're training it to say like, okay, you should answer yellow instead of this long sentence. And then the model gets confused, like, okay, maybe I should also answer yellow in the natural questions. So like just tell the model clearly on what your instance is. I think a rule of thumb is that if you are not if you are a human, you are a human, and if you see such questions, how you're going to answer. If you when you're given an instruction and you're not going to answer that way, then you should definitely reformat your instructions or the answers. And this is an overview of some of those existing instruction tuning datasets, and the field is growing really rapidly, and there are much more with different domains and also like different modalities coming out. Okay, so in summary, how are we going to teach multimodal models? And let's go back to this translation problem formalization. So we have different data. We have pre-training data. We can think of it as a dictionary that can teach those language models to understand the vocabularies from our new modalities. We also have instruction tuning data, which are short answer visual question answering data. those are like small puzzles that we can efficiently and effectively tell the model about some specific aspects, like quiz about a specific problem in some domain. We also have instruction tuning data sets, which are natural conversation, visual question answering. And those are kind of the real world applications that allow you to practice your skills and in a real world scenario. And this is how you can, with just instruction tuning, you may not be able to cover all the aspects of the capabilities that are needed. So you may be able to get something from the short answer VQA. And with just these two, you may not be able to cover all the vocabularies. So that's why you need pre-training. And without any of each, it may be hard. So yeah, that's it. And hope you enjoy it. And if you have any questions, I think we can take a few because like we still have lots of time left. Yeah, sure.
Do you think that reasoning itself could be framed as a translation problem? For instance, like if you reason, like here's my idea for a proof, and then you pass it into like a proof assistant or something like that.
So the question is like, if you can you formulate reasoning as a translation problem? And example you gave is like if we have a proof and like that proof like we want the model to basically like give some analysis or like
translate your idea is like here's a proof of the Pythagorean theorem, and then I'm going to translate it into a language that a proof verifier can understand. So I'm going to convert it into a program, right?
Mm-hmm. Yeah, so I think like for this part, we should like try to tackle think of this as like from two aspects. Is this some capability that the language model already has, or like you want to like or like can is this a purely semantic problem? So like we have our like if we think of our multimodal problem, there's a similar analogy there where you may be able to, if it's a pure semantic problem, you can formulate it as like a translation problem. You can think of it as like, it may be able to answer like some about the facts. But when you start to ask about the spatial details, like, which is kind of like start to reason, like what are the relationship between these two objects, which is hard to generalize from language only, then it's not a pure translation problem, like it does not automatically generalize, where you now need to like either fine-tune the model to do something, to try, because spatial reasoning is a kind of, also a kind of reasoning. Yeah, please.
No, what I meant was, suppose you have, or something has created somehow a program that's like, okay, is it on the left, right? So it actually already has a way of verifying, like it's a game engine or something. It says like, yes, it's definitely on the left, right?
Yeah.
So that if you think it's on the left, you translate it into inputs that this engine can understand. So translating from essentially like the language domain or the vision domain or whatever, the thoughts, in other words, of the agent, translating into something that actually can mechanically verify that.
Yeah. I think that's if let's say the like basically like now like basically like the key difference with this clarification is that the model is able to perform the reasoning, but you're only translating the results of this reasoning to some other format. But we cannot like translate like the reasoning process. Like if the reasoning process can be divided into sub-process, basically what we're translating are we're translating the states, but we're not translating the process.
But what I'm saying is that you might be wrong. Your proof idea might be wrong. But the thing is that the theorem verifier, or again the whatever this engine is that verifies a thing, it can verify a program with 100% accuracy. So your idea, your intuition about the proof may not be correct, but then like you put it in and you get feedback. You get essentially like a feedback from the thing that's going to tell you, yeah, it really is on the left, or like, now you're mistaken, right? So now you have signal in which your model can like adjust its behavior.
Yeah, exactly. I think this is like many current researchers trying to work on like how can you like use those formalization to like do the proper verification of those outputs, and this conversion is exactly the translation problem. Yeah. Cool. Should we just like if it's just the schedule, I guess I still have 10 minutes before the coffee break.
Yeah, and also before the coffee break, we also have a Q&A part.
Okay,
Maybe
cool.
you can just continue and
Okay. Okay, cool. Yeah. Any other questions? Or okay, cool. Sure. Do you mean like what types of the data will matter more for the model's generalization capability, or? Yeah. Oh, okay. So I guess like the key part is like how diverse your model is. Basically, what we generalize is we're trying to let the model generalize a distribution. And this distribution may be already something that the language model already knows, or it's some distribution that we want to teach the model to do so, or it's a joint distribution that we teach the model, which is something in the visual domain, and some distribution that the language model already has. So the key is diversity, like whether you can whether you can like approximate this distribution like with your training data. If you can approximate this distribution as much as possible, which is why we want to try to make those instructions more diverse and cover more domain as much domain as possible. And also that's why in Lava Next, when we try to add the user instructions, which are much more diverse because of both the inputs are diverse and also user image are diverse. And this way, like the distribution is like we find the generalization capability are like much better for those previous ones that are generated with like a fewer samples or in like a smaller distribution. Yeah. Should we get some coffee? Oh yeah, sure.
How would you make sure multiple data and line together? Like how do you know the detail is actually corresponding?
Yeah, that's a great question. So the question is, how do you make sure that the alignment that you're doing is actually aligned? And this is actually like, I think recent works are also trying to study this. One of the findings from those papers is that maybe like the model is performing great on those V2A benchmarks, but it may not necessarily be able to perform as well as those like zero-shot image classifications. We are using the CLIP models, but our zero-shot image classification accuracy may not be as high as the CLIP. So this is actually like one way to think like why, or it can be a metric to reflect on how well your model is aligning those distributions. But it also has another factor because when you're when we do CLIP like classification, what we do is like we divide this contrastive matrix and we use cosine similarity to manually compute the similarity and to map them into the label. So this part is deterministic, and we know that it will always output something that are in the distribution. But when you have an autoregressive model which can output anything, and you want to ask it to generate only a list of the 1,000 like categories, like in ImageNet, you can have two choices. One is like you you give it a long instructions and ask it only to output something from those 1,000 classes, and then you can do some like exact word matching, or you can use some perplexity-based metric to like measure like whether the ground truth target has the largest the smallest perplexity, like which one is it? But both will have some problems. So like so this is another problem on like when you're approaching this. When you're trying to approach this, you may have some problem on finding a proper proxy of this like alignment. Yeah, please.
I think the complexity metric doesn't work very well. Do you think it's because of all hallucinates, or is science like high probability to comment
I think one potential reason is that when the model, because we train the model with cross entropy loss, right? So what cross entropy loss does is that it only maximizes this positive sample. So it does. So when the negative samples are not the positive, although it can still reflect the like the model's prediction, but it's not as like trustworthy as the like top one prediction. And I guess this may be one of the reasons when the model is not predicting the target answer as the top one prediction. Maybe that can affect like basically the tail confidence distribution may not be that accurate, I guess. Okay. Oh, yeah.
So what do you think of is the bottleneck, current bottleneck part of the model? So we need better data or better visual encoder or language model?
Yeah, so that's a great question. So what's the current bottleneck of the vision language models? Maybe we can restrict to that so that it can be answered more easily and in a more controlled setting. So like basically, if we think of how the model is like built, like we have the vision encoder, we have the cross-modal connector, we have the language model. The language model will be mostly responsible for those reasoning related stuff. The vision encoder will be responsible for encoding proper semantics. So if we think of the encoder and the cross-modal connector together, then they both serve as like a single tokenizer where the information may be transferred properly. But but in our training, actually, like sometimes we're like freezing part of it, or the information may not necessarily be able to transfer properly. So that actually creates like a separate bottleneck for the semantic encoding because you're not actually representing the information in a way that the language model you can guarantee that it can process because some of the information may be dropped earlier by the vision encoder already. For example, if you just take a pre-trained clip or a pre-trained cyclope, you may find that it's not working very well on some low-level details because this is not the contrastive learning is enforcing. And it may be hard to just in reverting that kind of the property because they really favor the semantic in those pre-training. If you just pre-train it with some small steps, it may be quite hard to revert that. And there can also be a problem with like encoder-free like tokenizers where like but that also comes with another problem like whether it's just whether it's discrete tokens or it's continuous tokens. If it's discrete tokens, it also have some kind of problem like how much can you reconstruct the original image? That's the information lost in the beginning. So I guess like in summary, like all the parts of the modules may be responsible for some aspects. And I guess like because of this, like you may be able to make all kinds of the like improvements from each of them. Yeah. So yeah, so I guess this is also like the maybe one interesting aspect is like how you may be able to improve some aspect of some like component, and it may in turn results in a better like prediction of some other aspects you may not be expecting. Yeah. So yeah, I think it's a like unknown mystery that are waiting for us to explore. Yeah, please.
So you mentioned about this trying to retrain claim for safely using local information or texture information. So recently, I think the media have released the model of radio, so which they distill like SAM and and then I think IPF, which is the version of the into one quick H model. And then they have tested that on a level 1.5. But it doesn't really show a large improvement on the VQA benchmarks. So what do you think might be the reason? Is that because the way that we do or they do the training is not really reflecting those detailed features, or is that just the VQA benchmark is not reflecting their improvement on the like local information?
I think that's a good question. So if you like, so basically, I think the question is like, you have those VQA benchmarks and you have those models that have like great capability in different aspects, and how you can like how we make sure that it actually translates directly to the numbers in the benchmarks. I guess it's just hard because like you cannot control what the model does, and it may just behave here unexpectedly, maybe just because of randomness. It's also possible. But I guess the key is that like it's actually like I think it's really hard to develop a proper benchmark that is stable and also reflects the cues that you can trust and you can use it to understand like in a very deterministic way. Like so that's why we actually need like more and more benchmarks, but in a way that gives us like proper signals for us to improve the model. And it comes from both the aspect of the capability that you are trying to reflect and the how deterministical or how proper like it can translate to the real world capabilities. Even like you can see like I think yesterday there's a talk in the computer vision in the wild workshop where they try to find a correlation between different benchmarks and the different between the number of the benchmark numbers in the real world benchmarks where the user will vote for it and they compute the ELO score. Like for that, like you may see that some benchmarks are not necessarily reflecting the user's preference, but it's also probable that the user's distribution in those real world benchmarks are not it's also not the whole distribution that everyone will be caring about. So like it's just hard. Yeah. Okay, I guess it's time for coffee and we can also like resume the discussion in the afternoon session. No, I mean the like later session, there's a panel and also discussion.
Yeah. Maybe one more question. There is somebody ask a question online. Maybe you can answer like this.
The slide the presenter skips.
You skip.
Yeah, I guess like for that, like it's I think like different models will have different choices, like depending on what you need, I guess. So that's why like different paper will make different choices. How much like you require the language model to make like more custom decision to your task, and that's why people will make some kind of decisions. And also like this slide will be available online, so you can check out the details as well.
Okay, thank you everybody. So currently we are going into a coffee break and we will come back at 4 p.m. Okay, so if you are interested in somebody's talk, you can just catch them and ask some questions.
What is the breakdown that you know that what are your planning to put the schedule?
Oh, you mean schedule, right? Okay.
Is it just a panel discussion or?
Yes, I will let you figure out everything. Yeah. Right now, I think we are doing something to do with factuality and code, but yeah, we have certainly started doing multimodality with other clients. So I'm guessing that is what your focus is on.
Yeah, but like for more
Right.
Yeah, so yeah, I'm not sure how the deal is formulated. So I guess like, but definitely.
Oh, we can certainly start discussing those two. I mean, at the end of the day,
So what's kind of the process?
So there's no multimodal work we're doing with XO at the moment. At least, I mean, we first discuss, what you even want. But so it is definitely early with the but I think the most. So I feel like some of it is very, very kind of experimental. Things like recording the screens of knowledge workers and things like that. That feels a little bit more experimental to me. But there's one thing that's very hard. Yeah, which I'm seeing to be very. Maybe not the most thing, but I think the river is very hot. So, which is a direct image-based reason.
So
like now, for example, you could borrow bombs big time on the very basic reasoning involving graphs and things like this. So, yeah, are the remaining
live or is there hostile?
I think the following Roshan down is online. Others
unique settings in the world. So it's a very, very big talent in person. So it's helpful. We have a bunch of good automated testing. In fact, it's funny. We have had to adapt our testing also to make sure it is as LLM proof as possible. In fact, now about a bunch of, I mean, for code related tests, of course, there's a lot of specialized stuff we do. But for example, for things like the multimodality, people who can reason around graphs and visual graphs and things like this, we find that a lot of the
我刚把微信给退了，刚把微信给退了。
that involve images becomes key to implement it from GPT. So we will have to adapt that as when the test when the LLM statement is. So the step which will pick the very best people among that set. Then additionally, there are some key things also we do that is different from some other companies in the space. Like for example, we don't do the classic crowdsourcing. We think that
要不再发我一个，
in the sense that you have a giant pool, you can do one task, you can do 2 tasks, you can do 10. You only do one because it becomes very difficult to control quality if you farm up something to too many people. So
Yeah, that's also what we find. Like, we try to make sure that person is asked what's the task that he is doing.
Correct.
As much as it's.
Yeah, so first we find that you have to first, if you don't bring in people with the necessary skill and expertise, you end this school, you can't do anything. So step number one. We make the best tasks, we measure their accuracy.
我先下一下微信，太危险了。
Once they some time review processes. Now, different tasks there are some tasks which is a cheaper solution than actually doing the task. So in those, we directly have a
我的也是，我他妈那么老困了，太暖和了。哦，你也时差吧？我时差，现在是国内，国内过来。我在新加坡过来。
because you look at the research online yourself, you have to look at the corner cases that you're even looking at this. So in this case,
回去快弄了，回去睡觉了。太顶了，太顶了。
是啊，就是 in the first place. 你们来这边会do it and
我
他是他在美国，
我是老大的，还有那个，然后我是东北人，
我是 N 来的。
我现在是清醒了，你到晚上，
到晚上几点？现在已经
咱
晚上了。
6点该吃饭了，我该吃饭，我不能像我路上操。
Yeah.
像昨天刚说的，以前那边那个龙舟节，你知道吧？哦，对，我就看那个，那个确实，可以，可以。你们有 post 吗？我没有，你有吗？我有，就是一个，我等会儿发给你讲，看可以去看。可以。
Okay, cool.
东北大学，
对，东北大学。And you can
我记录。
It's in Vienna this time.
Definitely not.
Okay.
My visa to Canada is still pending. Like I applied 2 years ago.
Got it. Really interesting. Yeah, I'm planning at attending Musica also, particularly because of agents and IR and such. That
Yeah, I did not in the company outside the US. So, you know,
interesting. Okay, sounds good. Yeah.
Oh, yeah. 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 Oh.
Oh, 是门后天都写，对，OK。
Oh, yeah, I messaged you on Twitter.
我去看一下。
Yeah, I looked at chat. Yeah.
都不行了。
Matt? Oh, yeah, very interesting.
有机会多联系。
Actually, a couple of questions on that.
那那个突然太紧张，
You going to upload slide? Yeah, we will drop the slides later on.
Yeah, after that.
Okay. Thank you.
我说你太牛逼了，你说来，我操，不总细学习来学习，这刚刚我说你们这条路有后有多过分，我当时我都不知道咋回答了。我没听，从来没听过。我说你之前讲的时候说有什么，我还写扣的，
我靠，还有这个，
我说操，你这都来高到家，我没懂操。我说咱们在讲那么多东西，不能说你怎么能动作？报告比如推怎么能现在拉俩拉老师？
Oh, yeah. Yeah.
因为我过来的时候，因为他又在又讲了之后， 看一下这个突然有一个东西。那个放所以你们你们学校看完这个东西，明白？经历过经历。你们那个时候我可能有，这个我现在没有很多细节，有的情侣。
We have a constraint, like I'm saying, for example, you cannot just do like, you can just not like our video. 14, and then keep everything as it's a 4K video, like it's not possible for any of the person, even you screen and also like the training. So I think yeah, not innovations there, but also I feel like another so I'm really like this.
我有我一个人不懂用，我觉得太弄太那个。
Safety
control.
I think the yeah. I mean, like you need to have a proper way to ensure that you're it's okay for it's important for that. For example, you need to carry all the information that these are like have the main problem.
说不动，他们一直讲不能设这么多，你这么多方法，我这个用不上。然后那你们说你们前面有人在讲说大家都要分配，就是主要就是不是主要在或者就有一点像那个which they don't
Others,
so I think it was largely occupied. In order to get it largely basically passing for the that's it. No, actually, so
重启之后，然后在可以给我期限，以后干完以后，你们马上生物学家的电数学，但是我因为我看到之后，就是都太久了。
the thing about it,
你现在不这么难受，我懂你，现在所有人都要罚手，就包括我今天卖就这瓶那些，就是我当时我们其实就1个月就搞定了，就是感觉当时就赶了一批，在当时做点没错，但当时就是说一直放着，当时就给国内的企业有点阿特尔突然就这个调整，就这个调整。我感觉我不考虑思路，我说我再也不再一次。但是有的做那种，有的人要跟你说后面可能会给你做的特别别人保障。
So that's why我
本来就没有，我你发现了找不到我，我觉得你说如果跟你我不太了解做你，我真的说你已经可以做，那得期限。我现在讲真的靠不住，那种天气连休息，反正已经真的我可能都讲不一定会。给能给你说，可能给你多少钱？然后这个就是在这个期限上，期限
Oh, really? No, we have
Yeah, so this is the damage of 我现在我在上对吧？我现在办法是我现在回不了因为北德整个北德就把放弃的那个政策，我完全动不了。就是我主要出了病，就这个解决不了，然后我现在就是没搞，然后结果那就是而且不好，不是小生意，我觉得这个人心里不对，就是好像他每个人有权利。我现在。那个居留证就是居留证那个一般不会放房出去比较关注。Like you have two critiques, one and their loss is this is why this is why language apply. So some people try to directly insert the sun. 基本上好。但你不这些我自己一直租房吗？自己租，一直租房吗？我觉得拿着它那个就是。我觉得就是有时候有的就是他的身份就是这个最完美的最完美的。我不想回答，我是拉就是这个让我说。
But we're curious. For instance, for if I just want to have like tips of English, right? Yeah. Nothing with this do that on YouTube, right?
Oh, I see. So I think the main problem is the main problem is the translation strategy.
Yeah, it's the interest.
It's the the translation on the text side is the main problem with it is that there the problem is
Yes.
other things seem to be fine with me.
Yeah.
Yeah. So one thing we found in Lava is that it's able to gather different capabilities together. Even you one method really is that you scale up the multi-level OCR. You scale up the data. And then we can get a which is harder to scale, but you may be able to obtain that at least for a reasonable amount. And so you can get the basic really the other way is not to get about other problems, maybe USD.
They're like offices, they're on housing also. Yeah.
Oh, yes. So the problem. But I heard that there's TikTok
is more about data protection, so we are like more accessible data.
Oh, I see. Oh, I see. Ah, I see.
Yeah, also you mentioned that we have category prediction stuff. Actually, that's a real problem for us because we have like very long.
Yeah, exactly.
Yeah.
哦，在这儿。这个，嗯，嗯，是，对，我看我再重新搞一遍。我都没太重新。哦，那边本来就是大写小图，我们没有那个啥了。
It's clear.
还好，is it okay?
Yeah, it looks
Both groups.
perfect.
Oh, okay.
很差不多，got no right.
We have some small problems and we'll make some adjustments. 哎，行。
Okay.
Okay. So hello everybody. So our coffee break is end. So let's continue our tutorial, and Fu Xiao will continue to introduce the hallucination problems in multimodal language models for us. So welcome for Fu Xiao.
Hello everyone. Welcome back. My name is Fu Xiaoliu, and I'm a third-year PhD student from the University of Maryland, College Park. And I will talk about the hallucinations in multimodal large language model. So the question comes, what is hallucinations in multimodal large language model? 开一下那个视频。Okay. And generally speaking, hallucination means that refers to the phenomena that the general test does not align with the vision content. Just like the example right here, we give a question: can you locate the water bottle placed near the yellow tennis ball on the ground? And you can see the answer from different model like MinGPT-4 or like Lala 1.5. They just say yes, there's a water bottle placed near the yellow tennis ball on the ground. So that's a hallucination. So how can we categorize the hallucination? What are the different types of hallucinations in multimodal large language model? There are three types. The first one is called object hallucination. It means that the object mentioned in the text may not appear in the image. And the second one is called the attribution hallucination. It means that the object may appear in the image, but the attributes like maybe the size, the color, and shape does not align with the image. Just like the flower, the color of flower in the image. In the image, the color of flower is pink, but in the text, it's in the image, the color of flower is white, but in the text, it's pink. And the third type is called the relationship hallucination. It means that the interaction between the object within the image does not align with, well, so what are the behind the reasons of hallucinations in multimodal large language model? I just categorize the behind reasons into two categories. The first one is the hallucinations from the training data, and the second part is the hallucinations from the model. As for the reasons for the hallucination from data, we can have like maybe the noisy data, lack of diversity, and detailed description and statistics bias. And as for the model parts, it may come from the vision model and also language model, and maybe the cross model inference does not do well. I will talk about the details of each reason one by one. So the first one, noisy data. as we know that the multimodal large language model needs like two training states. The first stage is called pre-training stage, and the second stage is called the instruction tuning stage. And in the pre-training stage, we usually use the image test here stored from the website, and we do not do like the human annotation. So there must be some like the noise within the data. And then as for the instruction tuning data, just like Lullaby, we always use they always use like maybe the test only ChatGPT to generate the VQA. But actually, the test only ChatGPT does not understand the video content very well. Just like the example right here, you can see maybe like there's a total of eight individuals waiting for the train. But actually, after I check in the image, there's no there's no 8 people. So that's one reason that the noisy data which lead to the hallucination. The second reason is called like the lack of data diversity. You can say like for most of the instruction tuning data recently, most of the data only have like the positive instruction, but they don't have like the negative instructions with reject answers. So you can say we test the current model like maybe the MPlug and the Lullaby and also like multimodal GPT on a famous hallucination evaluation benchmark called POPE. You can say the percentage of the answer yes is very, very, very high. It's nearly like 100,000. So you can say even though you ask like maybe is there a dog in the image, so they prefer to answer yes. So that's like a bias problem. So what is the negative instruction I mean? I gave two examples in the right part. You can say like maybe can you spot a hot air balloon above the tall tree? But actually there's no air balloon in the image. So the answer will be like there's no hot air balloon mentioned in the image. This one is called maybe the negative object manipulation or something. Okay, another the reason maybe like the hallucinations from the vision model. Generally speaking, is like a weak vision model can lead to like the misunderstanding of the vision content. Just like the example, the first example, the document example, you can say the text on the document is not very clear, and the size of the text is also very small. So we ask a question like, what is the total cost of for the 5 cell size in the 0-5 years? And the model gives the wrong answer. So we can say like that is because the resolution ability of the model is not good enough. So they can't see it very clearly. And another example in the bottom, you can see I asked a question like, is the value of the X in the image 5? So you can see that the model just predicts that the model just misunderstand the triangle in the image as like right triangle, and then use like the wrong formulation to calculate answer. So finally it got the wrong answer like 5. So for these two examples, the behind reason is like the vision encoder is not good enough. Another reason is called the hallucinations from the language model. As we know, like in recent most of the multimodal large language models, they use like the Kuna or maybe like a Llama or some other models, as their language decoder. But the size of the language part is much larger than the image part. So like the model always tend to answer the questions based on its parametric knowledge memory. So you can see I also gave example right here. I asked like maybe according to the medal number of chart of 2008 Beijing Olympic in the image, does China have the most gold medal followed by the USA and Russia? And in our knowledge, we can say that China did win the most gold medal in Olympic Games in 2008. But in the image, we just make a change. You can say in the first row, we just change the gold numbers to 23. So we also mentioned in the question like please answer the questions in the image. But you can say in the prediction, the model also selects China won the most gold medals, followed by the United States and Russia. So you can say the model actually does not look at the image very carefully. direct, answer questions based on its knowledge. So that's what we call the hallucination from the language model. So after talking about maybe the behind reasons of multimodal large language model, so how can we evaluate the multimodal hallucination? Are there any metric or popular benchmark? So you can say I saw the hallucination metric. I just divided into two parts. The first one is like the LLM based, and then it's like the non-LLM based. And as for the hallucination benchmark, it also like two categories. The first one is like a discriminative task, and then the second one is called the generative task. So we can see I make a summarization of the recent most popular benchmark on to evaluate the multimodal large language model. You can see that for the task type, the GEN means generative task and the DIS means the discriminative task. The discriminative task means that the model always change the multimodal hallucination evaluation into like the yes or no question. Maybe like is there a dog in the image, or maybe is there a cat in the image, and the model only need to answer yes or no based on that. So, but for this kind of question, it's not an open-ended question. So for the generative model, it means like it's an open-ended question. Maybe like I will describe the image in detail, so the model can give like a detailed description of the image. So that's an open-ended question. Just like the example right here, you can see for the example in the left part is a discriminative task. You can say is there a bottle in the image, and then you can say the answer may be yes or something. So the evaluation method will only extract the yes or no keywords from the answer and then to say whether it's true or false. And the right part is called maybe the generative task, and then use the LLM-based method to evaluate. You can say by using the LLM-based method, you can the model can the evaluation method can not only evaluate maybe the relevance score, and also the relevance score means like the instruction ability of following, the ability of instruction following, and also the accuracy score means like whether the content in the answer align with the image well. So that's the difference between the two evaluation methods. And also you can say like by looking at looking at the table, we found like for most recent multimodal large language model hallucination benchmark, you can say the data source is from the mixed Google or maybe like VQA and also maybe the vision genome. But you can say we know that for some of the multimodal large language model, we have the mixed Google or maybe like the VQA in their training set. So in this way, when they evaluate their model on this kind of benchmark, it's not in the zero trust setting, because it maybe so it's not fair for other model, we do not use like the VQA or maybe like mixed Google in the training set. So that's why I recommend maybe a new benchmark called the hallucination benchmark, which is we got it from this benchmark is manually manually annotated by human expert, and which is an ideal benchmark for other models to evaluate, because it's in the zero trust setting. The source is from the website, it's not from Miss Google or maybe VQA, and also you can see the image type is very diverse. You can see not only have maybe the illusion image and also maybe like the poster, like Beijing Dark, or maybe like I can say the map of United States, and also maybe you can see the chart, and also like also maybe some OCR examples, and even some like multiple image examples. You can see this is also an advantage of our of the hallucination bench to evaluate hallucination, because like for previous benchmark, like maybe POP, like they only have maybe like object hallucination. So and they got it from website. So they have like common object, maybe like a human, maybe like dog or something. But in our design, we have like have diverse type of the hallucination example. So I think it's a better way to evaluate hallucination in the zero trust setting. So after talking about the behind reasons of hallucination in our large multimodal, and also like the popular benchmark in multimodal large language model. How can we mitigate hallucinations? So we divide the potential method into three parts. The first one is like the pre-correction, maybe introduce negative data, introduce counterfeit data, and also like maybe address the noise or maybe the errors in the training data. And the second part is called like the in-process correction. Maybe the techniques maybe like the scale up resolutions, or maybe like combine different weighting encoders, and also like a training related method, maybe like RLHF or something. And then the final method is called the post correction. Just like the wooden paper, I will talk about details in the next few slides. So the first method to mitigate hallucination is called introduce negative data. So, this idea is from paper LRE instruction. So this paper is designed to introduce both the positive and negative instructions for more robust instruction tuning. So you can see just like the example in the left part. The first 6 examples for the positive instruction may ask about maybe the, let me see, maybe the object detection task, maybe like OCR task. And in the, for example, in the bottom, you can see it have like different manipulation strategy, to introduce like the negative samples about hallucination. So you can see maybe can you force the eye burden in the image, or maybe like can you if the woman in the image wear like a pink pant or something, and then you can see in the as for the maybe the 2 examples in the bottom, you can see it's like the knowledge manipulation, which means you can see in the final example, the person, the woman, the lady in the image is Hillary, but actually we just change the name of the celebrate and then ask a question for the model. So this way it's like knowledge manipulation. So we also you can see in the chart as for the table in the right part, we try to fine-tune MinGPT-4 or maybe like unplug or on our data, and then evaluate on a popular hallucination evaluation benchmark called MME. You can see after fine-tune the 2 model on our data, the result on both perception task and also the cognition task increase a lot. And also you can see in the as for the chart in the bottom, you can see the accuracy of positive and the negative samples is also increased compared to the original like before. The result is not very good. And another mitigation strategy is called address noise and also like errors in the training data. It means like rewrite the text caption of existing image type pairs the data set by using ChatGPT. So the pipeline in the left part of the image, you can see it first extracts the keywords or maybe key knowledge from the text. And then you can say in the like the 17 words, and then use ChatGPT to rewrite the description of the image, and then use this kind of new data to fine-tune the model. And you can see the result on the right part. You can see they fine-tune like MPLAG or Lalava and also multimodal GPT and also MinGPT-4. You can see after fine-tune the model on the data, the performance improve a lot. So another method is called the scale-up resolution. In our mind, I think it makes sense like higher resolution usually result in a lower degree of hallucination. So just like the result in the chart, you can say we sorry, the format is weird because I changed a different laptop. Sorry. You can see in the I saw the table in the top. You can see we try different resolutions on our observation encoder, and and the basic model is Lalava. You can see if we increase the resolution of the weighting encoder, the performance will increase step by step. And also like you can see I saw the Laravel 1.5. We also like increase the resolution of the video encoder, and then we evaluate the model on different benchmarks like VQA, V2, GQA, and also test VQA, and you can see increase the resolution of the video encoder, the performance will increase. Format, so the format is weird. It's okay. Like I saw another method called maybe the training related mitigation method is called RLHF way. The method is like this. You know, it will first collect the human feedback in the form of the thinking segment level correction, and then use DDPO. DDPO means like the dense direct preference optimization, you know, to optimize the policy model against the dense and thinking semantic level preference. And the final one is called the post-hoc correction. Just like the model here, the wooden pepper, which is a training free model. You can see the example in the left part. You can see after they got the output from the model, they first, you know, extract the keywords, maybe or some key concept or maybe objects from the model, and then they use they just raise questions based on this key concept, like is there a person in the image, and what is the location of maybe the attraction in the image, and then they use like some external like extra models to answer this kind of question. So you can say they by using the expert model, they found that there's no people in the image. So that's they found that, you know, the people or the person object is actually the hallucination part in the original model, in the original output. So they just correct it. And you can see for the result in the right part, you know, the external results on NME, and they fine tune Laravel and also the outer. And the result after correction, you can say the total the total means the evaluation score. You can say the result is also increased a lot. So that's also a very efficient, because it's training free method, you know, to solve to address the hallucination in the model output. So sorry, ignore the benchmark. Ignore the slide. There are some format issues. So after talking about the behind reasons of hallucination in multimodal large language model, and also the famous benchmark, and also the metric, and how and also the mitigation method to solve the problem. So what's the future direction of the hallucination problem in multimodal large language model? The first one is called establishing a standard benchmark. So there are maybe the following category and criteria, you know, to build this kind of benchmark. The first one is easy to use, because, you know, like for the recent multimodal for recent benchmark, some of them, you know, will use like a large LLM, like maybe GPT-4, you know, to evaluate the result. But actually, you know, like it's always very expensive, and also, you know, waste a lot of time, you know, to run the code and evaluate. So that's not easy to use. So for the future direction, it will be like, you know, build a very easy method, you know, do not need to use like GPT-4, you know, to evaluate the result. And also like maybe the second category is called fire. I mean, like people can try to get the image from different source, not from like the common data set, maybe like Miss Coco, or maybe like Wikipedia or something. They can get data from different source. So in this way, people can really, you know, evaluate the model in a zero-shot setting. So that will be fair for every model. And for the third criteria is called the free form. I mean, like for the previous, you know, previous method, you know, to evaluate the hallucination, which do not need the GPT-4, it's like they just, you know, convert the problem into like a bandwidth classification task, like only yes or no. But that's not good, because like if you ask question like, please generate maybe a description of the image, And then, in this way, you will generate a very detailed description of the image. But you can't use like the binary classification task, to evaluate this kind of, free form result. So in the future, how to build make the evaluation method like free form is also very important. And also the final one is called cheap, means like we do not need to use GPT-4 anymore. And another direction maybe like receiving the hallucination as a feature. That's also a very interesting question. I mean, like, what is hallucination? Like, why do we call it hallucination? Like when we give a prompt to the model dream, and sometimes only if the content or maybe the fact in the model does not align with the image, then we call it hallucination. But actually, if the content is in the image, even though it's not correct, but it does not know about the fact or something. It's actually, the creation. Maybe it's creative. So how can we, build a model, to control, to control the gate of the maybe the threshold of the maybe creation and also hallucination. It's very important for the future. So, that's the end of my slide. So thank you for listening to my talk. And if you have any questions, we can discuss in the panel. And after my talk, let's welcome Zhuosheng Zhang to continue our talk.
But can you hear me?
Yeah, we can hear you.
Okay. So is there any problem?
Maybe you can share your screen.
Okay. Could you see my screen?
Okay, let me see.
Okay, yeah, I have been sharing my screen.
There are some problems in my side, so please wait 1 minute.
Okay, no, sure.
Okay, let me move the. Maybe you can open your camera.
Yeah, I have already opened my camera. Can you see me?
Okay, maybe.
Does it work?
Sorry, please some. So you open your camera?
Yeah.
Okay.
I can see myself in Zoom.
My side only show 废号 space. 废号. Sorry. Okay, so maybe I saw the camera and will show a camera.
Yeah, so showing how they.
Okay. Okay, it's okay.
Okay, great. So I will start it. Well, hello everyone. I'm Zhuosheng Zhang from STTU. Now let's move on to the 6th section. In this section, I'm going to introduce a topic of multimodal reasoning. Here is the outline. We will talk about 4 key topics in this section, including the basics of multimodal reasoning, multimodal chain of thought reasoning, and we will also discuss a hot topic. It is called multimodal LLM agents. And finally, I will summarize a few challenges about multimodal reasoning. Let's come to the first topic, the basics of multimodal reasoning. Here are a few examples of performing multimodal reasoning in our daily life. Picture is worth 1,000 words. So we often read figures and tables to perceive grounding information to obtain knowledge and answer questions. That means multimodal information can serve as grounding information in the input side for reasoning. Well, the other example is giving a prompt instruction. We can infer the intent and reason with our common sense knowledge and give a response with multimodal outcomes. This kind of problem often appears at creative tasks. We see that multimodal reasoning often means a process of deriving high-level conclusions from multiple modalities. It happens on either the input side or output side or both. For example, to answer the questions, we need to think about the supporting facts. And then we infer the logical steps based on the supporting facts and predict the final answer. There have been many forms of multimodal reasoning tasks that cover many disciplines, such as art, design, business, science, and so on. Just like the exams for human intelligence, those tasks are widely used for evaluating the comprehensive abilities of MLMs. So how to perform multimodal reasoning? First of all, we need to talk about foundational multimodal architectures. Currently, we have 3 major kinds of multimodal MLM architectures. As my partners have already introduced them in detail, so I just briefly summarize them here. Well, once the foundation model has been trained, no matter what kind of architecture is, we can use it to perform reasoning directly. On the one hand, the current MLMs are generally able to handle the interleaved inputs. For example, the images and text will be combined in a joint sequence, and we will feed the sequence to the model to generate the effective response. On the other hand, we can also use few-shot prompting to easily extend the MLMs to some diverse applications. For example, we can provide a few input to output demonstrations before the text problem. And the MLMs will generate the response by following the patterns in the few-shot demonstrations. This implies that current MLMs have got a strong ability of understanding and leveraging the context for reasoning. With the improved abilities of MLMs, we have seen that the paradigms of multimodal reasoning have changed a lot in the last few years. Previously, we need to train specific models for each task, such as image caption model or a question answering model. Now, a single MLM can generalize to a wide range of tasks as a unified model, and the ability can be further enhanced by in-class learning approaches, just we have already talked about. The second key evolution is from the single-step prediction to step-by-step reasoning. In traditional VQA problems, the previous model will only predict the answer without providing the rationales. Now, the MLMs have shown effective by first providing the step-by-step rationales, and then the model will use the rationales to infer the final answer. We call this kind of step-by-step reasoning process in multimodal scenarios as multimodal chain sort reasoning. Well, multimodal chain sort reasoning has many benefits. The first one is improved interpretability. We can offer the detailed reasoning steps to interpret the decision-making process, as this example shows right here. And the second one is improved controllability. When the step-by-step rationales are provided, we can integrate complementary information and modify the reasoning steps. And then we can use the improved rationale for the final answer inference. And the third one is improved flexibility. With the detailed rationales, it is possible to plug in external tools. For example, we can use a calculator to calculate the large numbers or use external retrieval tools to incorporate the external knowledge. And then we can use the plugin information to help the model to perform reasoning more effective. And in addition, a single MLM can also communicate with other models, and then we can use different models to communicate with each other to perform the reasoning. We are aware that multimodal chain of thought reasoning has many benefits. Now, let's dive deeper into the technical details in this part. The goal of multimodal chain of thought reasoning is to encourage the model to think step by step and formulate the intermediate steps before deriving the final answer. Well, in previous work, we often leverage a direct input to output format when performing when training a question answering model. Currently we have a COT format. There is an intermediate rationale step between the input to output mapping. For example, in the first work of multimodal chain of thought reasoning, there are two stages to perform reasoning. After we have the multimodal input, the model will first generate the rationale, and the rationale will contain the related information and the inference steps. And then the model will use the generated rationale to perform to infer the answer in the second stage. So far, the scope of multimodal chain of thought reasoning has extended in both input and output modalities. It depends on where the multimodal elements are introduced in which site. For input multimodalities, different modalities such as text, image, and graph are incorporated in the model's input. Besides using the rationale for reasoning, some work also first use a caption model to interpret the image, and then use the interpreted results as a rationale to infer the answer. So we can use different kinds of alternatives to in the input side to help the model reason step by step. Well, for output modalities, different modalities such as text and images will be generated in the output side. In addition, more recent studies have further introduced video of thought framework. Here is an example right here. It breaks down a complex video reasoning problem into manageable sub-problems, such as from low-level pixel perception to more advanced analysis, and tackles the sub-problems sequentially and then derive the final response. So why is multimodal chain of thought reasoning effective? Now, let's try to understand the role of multimodal reasoning. First of all, we would like to have a look at the role of multimodality. In other words, what's the role of multimodality in reasoning? Why do we need the accurate perception to perform an effective step-by-step reasoning? Here, we set up a baseline. Given that we have a multimodal data set with textual questions and paired with the images. The baseline model will only take the textual question as the input, and then it will predict the answer directly without considering the image. This is to imitate the scenario when the images are missing. In other words, the baseline is using the imperfect training data. For comparison, the other model uses the paired question and the image as input and predict the answer. This is an ideal scenario. Then we will compare the results in the science QA datasets. Here is the results. We can see that the baseline model performs performs much more inferior. It will suffer from hallucination because it does not see the image. Well, in contrast, when the images are provided in our idea model, about 60% hallucination mistakes have been resolved. Here is a more intuitive explanation for the phenomenon. For the same question with different images, the baseline model will learn many-to-one mapping because it does not see the image. Therefore, it is encouraged to hallucinate. Well, in contrast, when the images are provided, the model will learn more accurate one-to-one mapping, thus leading to more accurate results. And this analysis shows that introducing more reliable input, in other words, introducing if we can ensure the accurate perception, will lead to more convincing reasoning process because perception is the foundation for performing reasoning process. In other words, hallucination happens due to the inaccurate perception. Actually, the imperfect training data also always happens in our daily life. So ensuring the reliable input is very critical to ensure the efficiency of model training and effectiveness of reasoning in some sensitive scenarios. However, it will be useful if we want to use the model in some creative tasks. So maybe we need hallucination sometimes, but if we want to use the model in some sensitive scenarios, so we need to ensure the more accurate perception when we are preparing the training data. Well, next we move on the second exploration. We want to investigate the role of chain of thought. The working mechanism of chain of thought can be decoupled into two aspects. It firstly identifies the atomic knowledge components that are essential for reasoning process. For example, what kind of knowledge will be used to answer the specific question, and then chain of thought. The chain of thought process needs to integrate the relationships of the retrieved knowledge and construct the coherent reasoning steps. Generally speaking, we need to know what kind of knowledge that are used for the reasoning process, and then how to use the knowledge to infer the reasoning steps. Well, by breaking the complex problems into more smaller and manageable sub-problems, chain of thought helps gradually reduce the searching space for reasoning by means of the computation on more tokens. Well, the third role of chain of thought, multimodal chain of thought reasoning is making the reasoning process more correctable. By having the step-by-step reasoning process, we can leverage the external tools to correct the intermediate steps. In this way, we can overcome the ability defects of LLMs, such as large number calculation and seeking for more up-to-date information for perform reasoning more effectively. We are going to discuss another hot topic after we have known the details of multimodal reasoning. Then we are interested in how to extend multimodal reasoning for more realistic scenarios. For example, we want to build more powerful multimodal LLM agents. This is the topic of this part. Currently, many people are blaming that LLMs are as the brain in the vat. This is because their strengths are often limited to content-based reasoning, such as question answering and content creation. They do not have interaction with the real physical world. Fortunately, with the ability of multimodal perception and strong multimodal reasoning of MLMs, it is possible to build autonomous agents to interact with the environments and solve complex problems in the real world. Those agents can follow language instructions and execute actions in environments such as physical and virtual environments, and they may use tools if available. For example, they can use API or use the programs to execute the actions. Ideally, they have 4 key features: general, autonomous, adaptive, evolutionary, and socialized. Here are some typical applications of the agents that have been widely used in complex tasks that are very hard for traditional deep learning models to solve end-to-end. For example, GUI control, scientific discovery, software development, and multi-agent collaboration. Depending on the roles, there are 2 typical kinds of agents. There are autonomous agents and communicative agents. Generally speaking, autonomous agents are able to solve complicated tasks autonomously, while the communicative agents are personalized and socialized agents with human behaviors that can communicate, collaborate, and debate with each other. Here are a few examples for autonomous agents, such as mobile device automation, web page automation, and application automation. The communicative agents are personalized, socialized, and interactive. There could be agent-to-agent collaboration or agent-human collaboration to solve complex tasks. Here is an simple overview of a single agent system. Once receiving a user instruction, an agent needs to complete the task with multiple steps of interaction across the environments and possibly operating with specific tools. And the agents also needs to make plans and take actions and operate in each round of interaction. And then we'll perceive the changed environment and update the whole operation workflow. So far, there are 2 key research lines in building such an agent framework. One side is improving the foundation model. For example, how to achieve more accurate, efficient, and comprehensive perception in the complex environments. Not only the content-based question answering scenarios, we also need the MLMs can understand different kinds of environments, such as GUI screen or the more fine-grained perception of the physical world. And the other research question is how to make the model more effective at handling and reasoning non-context and keep them consistency. Because in the agent framework, the agent needs to interact with the environments in a very in many steps. So the context would be very long, and the model also needs to infer the action based on the action history. So there will be more severe non-context reasoning problem. And for the second research line is workflow. We need to help the agent how to perform the action step by step, how to make plans, how to make the decisions. So we need to develop a workflow to solve a complex problem. In the workflow, there are many elements such as perception, planning, tool use, and interact, and make memory mechanism. Also, maybe some scenarios need the collaboration of different agents. So we will also consider multi-agent collaboration. Now, let's have a look at a systematic example of multimodal agents. We develop Auto GUI. It is a multimodal autonomous agent for GUI control. Given a user instruction, the agent can help users in completing tasks in distinct environments, such as operating systems, specific applications, and web browsers. In each interaction, the agent needs to imitate human behaviors, such as clicking, scrolling, and typing actions, and then operate directly with the GUI. Well, Auto GUI leverages a COT style workflow. We call it chain of action. A chain of action has two parts in the procedure, including a chain of previous action histories and future action plans. The key idea is to leverage intermediate previous action histories and future action plans to imitate the memory and the planning mechanism of an agent framework, so as to help the agent decide what action to take in the current step. How is the performance? Auto GUI achieves state-of-the-art performance with action type prediction accuracy of 60%. And the overall action success rate is 74%. It can be adapted to different scenarios without the need to train specific models for each task. It covers over 30,000 unique instructions and 350 apps and websites. It also does not need additional annotations and it's very easy to use. It can interact with the GUI directly without needing to accessing the API or specific tools. Well, we have found several insights in this work when we in the view of multimodal reasoning. We see that changing the vision encoders influences the performance dramatically. This means that vision features are very critical in GUI tasks because GUI involves comprehensive elements, for example, interleaved icons, text, and boxes. So the imperfect perception of the GUI may mislead the reasoning process. So in the future, we may need more fine-grained perception in some specific scenarios, such as GUI or physical words if we want to develop more powerful MLMs. Well, in contrast, model scale tends to be less important in this task. We have seen that using larger model do not improve the performance significantly, but the perception influence more dramatically. We also calculate the category results to see if Auto GUI can predict both of the action type and action details correctly. For example, if we predict the action is click, we also need to know if the clicking space is correct or not. According to the results, we see that Auto GUI achieves over 90% action type accuracy on average. But the major mistakes are about the click regions and scrolling directions. That means the model tends to predict the predict the action type correctly, but it does not know which space to click or which direction that the model needs to scroll. In other words, the model knows what to do, but does not know how to do it accurately. This is also, we guess this is also a problem of the perception because it does not fully understand the GUI screen. Now, let's have a look at the challenges in the view of multimodal reasoning. As a very important part of MLMs, multimodal reasoning still faces some unresolved challenges. It is very promising to expand it to more broader and comprehensive scenarios. There are emerging studies in terms of evolutionary reasoning, interactive reasoning, and reasoning alignment. With those studies, we hope to make MLMs be able to actively explore and evolve from environments and allow human in the loop reasoning process and help the model to make more accurate decision. And then once the multimodal LLMs have become more powerful, we also need to ensure the safety to evolve the model, avoid the model making any harmful behaviors. These aspects of studies involve both the ability of the foundational abilities of MLMs, as well as the reasoning workflow that we may design once the model have been already trained. Well, let's conclude this section. In this section, we first introduce the definition, background, and development of multimodal reasoning. And then we dive into the triggering multimodal chain sort reasoning. And next, we go to another hot topic, multimodal LLM agents. And finally, we highlight the remaining challenges in future that we are interested in future studies. That's all for this section. Thank you. If you have any question, we can discuss later in the panel session.
Okay. Thanks, Gusheng. So, okay.
Okay, let me share screen.
So is this okay online?
Yeah, I think it's good.
Okay, so let me begin. So hello everybody. I'm Zhang Ao. I'm a third-year PhD student in the National University of Singapore. Today I will make an introduction to the efficient multimodal large language model. So today I will introduce this topic in the following aspects. First, I will make an overview about the topic, and then I will introduce some efficient architecture designs that may be useful for saving the cost in either the training or the inference. Thirdly, I will introduce some observations from current SOTA models data compositions. And later I will introduce a training strategy, and also you can use smaller models to reduce the cost. And there are also some techniques that can be used for the efficient. Okay, so let's go to the overview. So before going into the concrete topic, let's first make a definition of the efficient multimodal large language model, because so I try to give a definition. So it may be like this. So given a target performance, we want to reduce the cost for the training and the inference. So because if we want to get a better, a good multimodal large language model, we don't want to degenerate the performance.
Sorry. Oh, your screen does not change. It is still in the first place. So is any? Yeah, maybe there is some problem.
Okay. So let me check.
So it also doesn't change, right?
Yeah, I think it is not in the right screen.
Okay.
I can only see the unwindowed. Yeah. I think it has been changed to the there are a few words CVPR tutorial.
Okay. Let me share again to the different view. Okay. Is this okay?
This is in the speaker mode. It is not the full screen mode. Yeah, I have send you the screenshot. You can see that.
Yes, I think you can click the left top of the screen and switch to the full mode.
Zoom 里面不对是吧？对对对，Zoom 不对。我要不改成 Miro 的，Miro 这个。对对对，没有变。我在哪？哦，这里只需要这个一个不是那个颜色。不是，我得先改那个 Miro 关。我这个在哪儿？Miro，这个这儿吧。Sorry for that. 你要不帮我搞一下，我有点忙。找那个。
Sure, that's the previous time. Share that's the two, and then just make full screen.
Hello, is this okay online?
Yes, it's okay now.
Okay, let me continue. So, we first try to give a definition of the efficient. So given the target performance, we want to reduce the cost for the training and inference. For the architecture part, there are some efficient architectures, especially for the very encoding part, there are some things we can talk about. And there are also some observations in the data conversation. And for the training strategy, you can use things like the transfer learning or connecting your large language model to some pre-trained tools or other models. You can reduce the training cost for the functionality extension. Okay, you can also use the smaller models. There are also some other techniques like you can use the DeepSpeed or some other tools for the training acceleration. So first, let's go to the architecture part. So for the very, I think the main things that can accelerate the training and reduce cost for the architecture part mainly lies on the very encoding. The background is that the high resolution is a key factor for the multimodal large language models performance. You can get a lot of recent papers like Apple's ML1 or the IDE Fix 2 by the Hugging Face, and they all talk about that. The high resolution is even more important than the size of the parameter size of the VIT, which is a very encoder. And however, the high resolution will naturally lead to a significantly more tokens, which is computationally expensive. Let me give an example. For example, we can say that given a clip, the normally used clip VIT large, which is a popular very encoder choice in the MLMs. And if you use the resolution like 200 multiplied 200 like this, you will have the 256 tokens. But if you if you increase the resolution from this one to this one by 4 times, and you will also get the 4 times tokens. When the 4 times tokens get into the large language model, especially for the cycle attention part, it will naturally get around 16 times cost. Okay. However, it's a key factor for performance. So how to reduce this? There is a method is that for the very language models, they typically introduce things like compression layer. And previous presenters also maybe talk about this. They maybe call this a predictor or connector or some other things. So there are ways for compression. Okay, so let me introduce some old models that with or without the compression layers, and from the older one, we'll gradually get into the new ones. So what is the change? So for the older models like the Blip2 or the Blip2 use a Q-former for the compression. It can comprise like the 256 tokens into the 32 tokens, and also get a good performance. And for some other models like the Lava or Lava 1.5, they don't use the compression, so they will typically result in more tokens. And however, what is the problem of the Q-former? Because we know that recently the Q-former is not such popular like the 1 year before. So recently, the new models all changed to new patterns. So what is the problem Q-former? If you go through the original Blip2 models paper, you will notice that the Q-former is actually a first level model, like 300 million parameters, and it requires a pre-training. If you don't conduct the pre-training on the Q-former before in a very intensive way, the performance will get a degeneration very significantly. So how to eliminate this kind of problems? The solution one is that it's a highway connector or highway compression layer. So recent models just replace the highway compression layer to a lightweight one, to a lightweight compression layer. Okay, let me give some examples. For example, there are some new models like 7VL, Mini CPMV, and IDE Fix. Okay, what they use? They use one layer cross attention. You can also say other names like the perceiver sampler or some other things. The idea is use cross attention to just encode the lot of variable tokens into the smaller amount of one. And also there are some other ways like the mini GPT v2 or the 5.3 variant. So their idea is that we can merge the JSON tokens with a linear layer. I use the mini GPT v2's figure for example. We can say that some adjacent variable tokens can be grouped together and concatenated, and then we can pass them in with a layer, a single linear layer or some other very lightweight layers. After that, it will get a reduction like 4 times or 16 times in the variable tokens. There are also code agents use a slightly different one. They use a low resolution features as a query, and the low resolution features can be used to query the high resolution features. I try to give an example like this. Okay, we can say that there is a low resolution image input, and the low resolution image input get pass the image encoder and get some tokens. After that, there is also a high resolution input. They also get a high resolution encoder. You get a lot of tokens, but the lot of tokens, if you directly feed into the decoder part, very long range decoder part, it will be a very high computational cost. So they also use cross attention, and cross attention can use input image low resolution features and queries to query to incorporate the features from the left side one, which is the high resolution one. Okay, so after talking about the lightweight compression layers, there is also another parallel and also typically used in company with the compression layer, which is the image slicing strategy. So what is the image slicing strategy? The image slicing strategy is to split the high resolution input into several grids or slices. Every slice will then pass the VIT separately and get their features respectively. All the features will get flattened or combined together into the large language model. So what is the benefit? The benefit is that because the high resolution, like over 1,000 multiply 1,000 resolution is not pre-trained for the VIT. So it can reduce. But if you get a slice like pre-trained, which is similar with the pre-trained resolution with the VIT, they can significantly reduce the training gap. So it can accelerate make it easier to train for the VIT to encode the different slides. Okay, the second advantage is that the VIT can process each slice separately, and that can reduce the cost. Because if you fit all the very high resolution input image into your VIT, and your VIT part will also get a lot of tokens. There is also a self-attention in the VIT part. So if you just use the slice, it will can also reduce the cost in the VIT. Okay, so I try to give some examples that use the slice strategy like the Sphinx MN1, Lionix or Mini CPMV 2.5 or ID Fix 2. So there is also another things we can talk about is aspect ratios. Because they try to make the slides, but they don't want to change the aspect ratio too much. Because if you change the aspect ratio, imagine that you have a square and you change the aspect ratio, it will become a rectangle. So it changes what you say. So there are also some strategies to keep the aspect ratios. So the first one is just use the padding. Like we pad the image into a square and then we conduct the slice and everything will work. The second one is that you can just use the position embedding interpolation because the slide, the idea is that each slice is not a square. It's not according to your pre-trained VIT's resolution. So you just keep it different and use the position, just interpolate your position embedding. Okay, so what's my opinion on these two different strategies? I think maybe the position embedding interpolation one will slightly get more training cost, but it will be more friendly when the input image in a very extreme aspect ratio. Because if your input image is very, very long and you just use some padding, like there will increase a lot of unused computations on the paddings. Okay, sorry for the mistake. So after that, we get into the data part. So what is our observations to train our model efficiently with data? So I think the idea is quite simple. The usage of high quality, like the human annotated data, significantly boosts the multimodal large language models training efficiency. Let me give you an example. Like some old models like Split 2 or Well Tuna, they use web captioning or some captioning data, and they will get MME like this way. But however, some new models we like Instruct Deep or Lava 1.5, we incorporate some more human annotated data like VQA V2 or GQA or other a lot of combination of high quality data, and they will easier get higher MME with lower training costs. Okay, so I also try to list some widely used high quality data sets for different targets. Like for the general VQA, we have the VQA V2 tool, or things like SenseQA, VGQA. And for the OCR, we have the text caps like the Archive QA and things like that. And for the instruction tuning, we have the shared GPT-4V, and recently I had an update on the slide. We have shared GPT-4o or things like that. And LRV, this kind of thing is very useful if you want to train a model efficiently. And for the reading understanding, there are also some things like the Coco series, Flickr entities, and for the pure text. Actually, the pure text is very important in the multimodal large language models training. If you don't, I guess currently the SOTA models all incorporate some pure text models into their training because it can significantly, increase your model's response length or response quality. Okay, so let's go to some cases. Okay, so data ratio is important, but limited works on how to set it. So to explore or to illustrate some key factors on the data ratios, I try to investigate some recent models in the open source community that with very good performance that may be comparable with some previous cloud models like the Gemini Pro 1.5 or GPT-4V. Okay, so this example is InternVL 1.5. It can obtain a similar performance with this powerful models with 26 billion parameters. So what is the data composition of this model? So empirical observation that there is a higher ratio of the data with long text, VQA, and OCR, or because the OCR is important for some downstream data benchmarks. So of course you can, if you want to go to other important capabilities, you can just replace them with something you want. Like the data set used in the pre-training stage for InternVL is that the OCR part, we can say that it uses a large portion of OCR, like 32 and 8%. Okay, so there is also another recent powerful model named Mini CPM Lava 3 V2.5. You can also get similar performance with like the Gemini Pro or the GPT-4V in the last year with only 8 billion parameters. So the data composition is also we can observe similar things that it's with a high proportion of the VQA and the OCR and the chat. The chat is the real dialogue, which is a long response. Okay, so the long response will make your model things to be more user friendly. And also because it have different parts of training data, especially the part two is near to the end of the model's training. It will show more important play a more important role in formulating the model's behavior. So we can also see that they use a lot of instruct data, which is conversation and long response, and also a high quality, high proportion of text only data. Okay, let me make a brief summary. The brief summary is that use high quality human entity data or GPT generated data and increase the ratio for the data with long text and VQA and also the OCR. Okay, for the training strategy part, I need to be faster. Okay. So for the training strategy parts, the first idea is that we can use things like the transfer learning to transfer some existing models, existing parts of the pre-trained models or the pre-trained multimodal learning models to the new ones. This model, this strategy is, this paper is based on the previous Flip 2 model. It's somewhat get outdated, but I think the idea may be also useful. Okay, so the idea is quite simple. So you already train a value encoder or the value part on an existing large language model. So when you get a new large language model, like the bigger one or type B one, like currently you have the OPT, tomorrow you have the Llama 3. So we can just move or transfer the value encoder part to the new large language model. Okay, so the idea is quite simple, like you can, it's a two-stage training strategy. Okay, so maybe to save the time, I skip the details. Okay, so what this can achieve is that we first validate the performance, the model on the Believe 2 training. Okay, so the result is that we can reduce the cost from over $2,000 US dollars to around $100 US dollars. And also, the final performance is do not get degeneration, and also even sometimes you get a better performance. This paper is at the last year's, similar to the period of the mini GPT-4. So at that time, they also build a conversation model. And the model conversation may be like this. Where is the place in the image? We connect the model to the where tuna. Okay, so we can ask the place in the image is, they can answer the place in the image in Singapore, a city state located in the Southeast Asia. So why do you think so? So because they recognize the MBS hotel in the image. And also you can ask, okay, what is the cost of staying in the MBS hotel? So they can tell you it's around $300, but they also ask you, okay, you need to actually check the website. Okay, so they can also tell you, okay, the website is this URL, and I also take a try. The website is the correct website. Okay, another training strategy is that we can connect your pre-trained models to some tools or some other pre-trained models to reduce your training costs. Let me give the localization task as an example. Like for the traditional way to enable your multimodal large language model to do the localization task, like the segmentation or the post estimation or the detection, we need to use the pixel-to sequence strategy. So they like the model to output everything as text, like the bounding box coordinates, or for the segmentation, you need to output the object boundary points. Okay, so to achieve the goal, you need actually a costly training. So how to alleviate this? Idea is that we can connect your large language model with some tools with the embedding and for the efficient functionality extension. This is also a similar idea with the next GPT. You can connect the model with tools like the SAM. with the embedding, or you can also combine this with some other tools like the image diffusion model or the video diffusion model or the audio diffusion model to extend the model's functionality very efficiently to the new tasks, like the segmentation or some generation tasks. And for in our example, we connect them with the SAT model, and we can see that we can easily get a library training. We can get output bounding box and segmentation masks for the given image and the query or something else. Of course, to save the cost, a very straightforward way is that just replace your model with a smaller model. It already easily works. Okay, and also by analyzing and observing the recent trend of the community, we found that with the increase of the time, like the models that achieving the similar performance with the last year GPT-4, will get smaller and smaller sizes. So we also believe, we think that something like the Moore law in the multimodal language models area. So it's very similar. So the idea is that with the developing of these models, we can get smaller models with strong performance. There are some examples, like the mini CPM V2, 2.8 billion, and it can get a similar performance or even better performance than the EVL 34 billion. And also, you can get a 5-3 variant model. It can also get a very good performance compared with some 7B or some unknown size models. Okay, there are also some other techniques, maybe more related to the training and the code. So I will quickly go through. So, for example, I think if you train a multimodal large language model or large language model before, you will be familiar with kind of techniques. Like you can use the deep speed or the FSDP. It can sort the optimizer states, grading model parameters into the different CPU, and you can reduce your training cost, and already become I think a common practice in training the models. And I try to make a very brief comparison. The FSDP is just installed with our PyTorch, and but not so flexible like the deep speed. Because deep speed has different stages, you can just configure them by hand. And the advantage is that more widely used and flexible choice among 3 stages. And of course, a very small disadvantage is that you need extra installation. There are also some other things like widely used practice, like you can use lower precision, like bflops 16, and the gradient checkpointing for training or CPU offloading or the quantization for the inference and for the data loading. If you really want to go through the pre-training or the video pre-training, this kind of things. I think the splitting the images into small files is not a wise choice. You can use something like TSV or the Parquet, or of course you can write something like the prefetch, or you can because your training data will have very different predefined very different lengths. You can also use some techniques in the large language model, which is the packing multiple data items into a predefined max length. Like different from this, you can just padding the items together. Okay, so to summarize, for the model architecture part, the higher solution is important, and you can use the lightweight compression layer and the slicing to reduce the cost. And for the data, you can use the high quality data and the high data ratio for some important data combinations. For the training strategy, you can use the transfer learning, the high the pixel to embed patterns for functionality extension. You can also use smaller models. For the techniques, you can use kind of blah blah techniques. Okay, so that's all my part. So maybe let me see. So Prof. Taiwan. Oh, maybe if you have some questions, you can just catch me after the talk. Currently, maybe we just go through into the panel session. Okay, is this okay? Okay, so let me stop sharing and contact the Prof. Shicheng.
Hello.
Hi, Prof. Shicheng.
Yeah, I'm here. Yeah.
Let me open the video and let's Prof. Han Wang to get into the camera. Okay, so maybe you can get into a camera.
Hi.
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 Hello, everybody. Hi.
Hi. Maybe change the. Okay, maybe it is okay.
Yeah, it's okay.
Okay, so before that, I may ask some questions maybe interested in to the two professors and other talkers presenters. Okay, so let me find the questions. So I think the first question is that what is the real path towards the AGI?
I think maybe we should start from our remote speakers, right?
Oh yeah.
Yeah.
Okay. Remote speakers. Prof. Han Wang think we can begin with some remote speakers like maybe Prof. Shicheng is interested in the question. What do you think is the real path towards the AGI?
Yeah. So when we say AGI, the definition is not so clear. Some different people have different explanation definitions. Yeah. So for me, so basically, I have some feeling or belief. So one belief that AGI must be multimodality. Yeah. So if just one modality, this is impossible. Maybe I use some figure to use a PPT to share some ideas.
Yes, Prof. You can share your screen.
Okay. Yeah. So this is a PPT. Yeah. So so when we say, for example, the AGI, we expect AGI can be very similar to human. Yeah. So but human, a very important property is a consciousness. Yeah. But what is consciousness and the definition and how the consciousness works are still unclear to the researchers. Yeah, but the people in the psychology already have some explanations, and they proposed a metaphor called as a stage theory. But they call this actually the whole framework as a global workspace theory. So the idea is that for neural systems, for the human, we have different for example, subsystems, for example, for vision, for speech, for touch, for temperature sensing. And all these different subsystems may be sometimes like one foundation model, but this is not the consciousness. Yeah, so means consciousness means actually for human, besides this kind of system one systems, there is another system called as system two. System two is like a stage, and you will have some director will use attention to select what kind of signal should be bringing into the stage, and extract the memory, extract, for example, the intention, the predefined intention, and also extract some tools. And then all these things are put into the stage and then do the reasoning. So means this reasoning process is called as the consciousness experience. Yeah. And then the output will be broadcast to all these different subsystems. Yeah. So this kind of systems is called as the consciousness experience. So I think this can explain how maybe possibly how the AGI works. Yeah. But so when we, for example, translate actually into the artificial intelligence language, it will be look like a super agent. So means a super agent use attention, use use memory, use tools, and use dynamic reasoning, and then also have the access to different this kind of multimodality foundation models. All this together actually will be the maybe possibly the ultimate form of the AGI. Yeah, so means I do not believe that a single modality of the foundation model can be considered as AGI. So means different modality of the foundation models together plus a super agent where maybe will be the path for the AGI. So this is my personal actually feeling and understanding. Okay, I just said so much. Yeah.
Okay.
Thank you, Bruce.
Thanks for question. So, hi, Prof. Haiwan. Do you have some opinions?
Yeah, to save time, I think my opinion is that the path to AGI is via NVIDIA. Yes. You got me.
Okay. So very insightful comments. Okay, so maybe maybe we can come through the next question. So the second question is that what should the human level AI system will look like in the future? So like maybe for the architecture, is this a large language model, autoregressive large language model, or the diffusion model, or other things, the two processors or other presenters think, what will the human level AI system look like? 我还是让他先开。Okay, maybe we can also ask Prof. Shui Cheng's idea first. So how do you think
maybe you start from Fei Hao, yeah.
Yeah. Fei Hao. Maybe you can talk about what do you think about the future human level AI system look like?
Okay.
Maybe I will give a very simple opinion. I think that maybe currently the most possible form is something like the Figure 1 system from OpenAI. This maybe is currently the best system we can observe from the whole world. Yeah, so means it's an embodied system. Yeah, so means include the hardware and the software and the multimodality intelligence, and can well control actually the robot actually to interact with the world. Yeah. Okay. Thank you.
Thank you.
So the question is human level.
Yeah, what do the human level AI system look like? Maybe you can talk about either the high level or low level, like the architecture.
All right. So I think the first thing is because we don't have a unified multimodal LLM. So I think the first thing is we need to, if we believe in that autoregressive is the future, then we need to, the first thing is to tokenize everything into a good tokens, and we'll train them in a everything as autoregressive, and the next token prediction will be the world simulators. Yeah, so I think of course the future human level AI is a world simulator. Yes.
Okay, so thanks for Prof. Haiwan's idea. So I strongly agree with Prof. Haiwan's idea. So because currently we see that the path towards the AGI, maybe the autoregressive large language model seems to be a promising one. But if we want to incorporate more modalities or learning from new modalities like video, because video contains a lot of word knowledge, yes, we need to tokenize the video first. And after tokenization, we need ask the design the tokenization and the proxy task to be difficult enough to learn the knowledge. Like because if you currently you only tokenize the image into different patches, you want to recover the patches. We all know that in the MAE, you need to set the mask ratio in very high mask ratio like 70%. So we also need to design the tokenization and ask the autoregressive task to be hard enough or difficult enough or meaningful enough to learn the new knowledge. Or maybe Fei Hao, do you have any other ideas about this?
So okay, so thanks for raising the question. I think I'd like to answer the question about the like say language now serve as a way to learn the intelligence. What will be the role for other modalities, right? So currently, almost all MLMs are primarily built upon the language type intelligence, right? And actually utilize it as the core framework while integrating other encoder or decoder to understand or even generate output in other modalities. So in sense, the core of today's AI, I mean the MLMs, you know, predominantly it centers around the language intelligence. But I believe so much that the true AGI, or say the human level AI, should not be biased just towards language, because the intelligence can be learned through any modalities. Let's imagine how we human come to play. All modalities should play an equal role in facilitating the learning of intelligence, right? So I think that the future developments in the MLMs should involve extensive pre-training on the large scale multimodal data. Is pretty much like the training approach used for the the language based LLM like ChatGPT. So this would ensure that these systems can leverage the full spectrum of modalities, right? Not just language, to achieve a more balanced and comprehensive form of intelligence. Yeah. So by this way, we would potentially move us closer to realizing the real one, the realizing the AGI that mirrors the human cognitive capability more accurately. But so what are we facing now is the key question: can we repeat the miracle of ChatGPT moments just to the multimodal MLM, right? So this is a question, the real question. Yeah. So we don't know if we can repeat the miracle of scaling law on the multimodal data set. Yeah.
Yeah.
Thanks.
So yeah, so I want to add something. Yeah. So I partially agree with Han Wang's opinion that if we can, for example, tokenize everything and then next token prediction can be a very good way, for example, to mod actually the reasoning process. But for some, for example, capabilities, for example, mass calculation. Yeah, so maybe the underlying logic for human brain actually maybe is not run in this way. It's not a next token prediction. It's more like a logic. So means in the human brain there will be some very particular this kind of architecture, a neural subsystem for this kind of mass calculation. Yeah, so it's not maybe it's not based on this kind of tokenization process. Yeah, this is my personal opinion. Yeah.
Okay. So yeah, I still have one question.
So means besides the, I mean the major this kind of next token prediction model, maybe there will also some other particular form of the tools or APIs which can be called to accomplish, for example, some particular tasks, and then all this together will be the ultimate form of the AGI or the human level AI. Yeah.
Okay.
Do you want to respond to the profession's idea?
I agree. Yes, I don't think AR is the only way, but because right now I think the most advanced AI is in AR. So if I have to choose to believe something, I choose someone existent. Yes.
Yeah, for example, yesterday I think one paper was released from He Kaibing. So means whether AR need a tokenization or not. Yeah, I did not carefully check the paper yet. I think at least the title is very interesting. Yeah. Yeah. So maybe next token prediction is right, but this kind of quantization process may be unnecessary for some scenarios. Yeah.
Okay. So I have a question, professors. So do you believe or say will the final human level AI still data driven?
Here the data means, for example, the real world data or include this synthesizer data.
Both. So this question is very tricky. I mean, yeah, will the final human level AI still data driven? I also static data or real world data. What's your viewpoint? Do you still believe we have enough real world data, or say we can leverage the static data, right?
So Hanwang, maybe you go first.
Yeah, I think yes, I believe that the future data tells everything, and synthetic data. Well, I think it's a philosophical question, because if the large models can capture everything in terms of data, then the data is generated from the model, and anything generated by some artificial intelligence is synthetic data. So in the future, there will be no boundary between synthetic and real world. And maybe there is a very popular philosopher that says that maybe the human being living in a simulator with 99.99%. Yes. So maybe we are just NPCs. We are synthetic.
Yeah. So Personally, also I believe the synthesized data will also be very important. Yeah. So for example, for just for human, right, in the learning process, sometimes you will you look at for example a textbook. Actually you will self-thinking, self-reflection. So means this kind of self-thinking or self-selection process, I think some new data have been generated. Yeah, so means beyond actually the data you capture from the textbook. Yeah, so means in the human brain, this kind of self-reflection, self-thinking, this kind of process is the intelligence evolving process. Yeah, so means maybe in future when all the real world data have been utilized, and then the next step is that how the foundation model or the agent can, for example, use self-thinking, or maybe, for example, the self-play. So means one agent talk with another agent. This kind of process, maybe some new data which can lead to even high level, this kind of intelligence will be generated, and then the intelligence evolving process can be modeled. Yeah, I'm not quite sure what kind of process can really do these kind of things, but intuitively, actually, this kind of, for example, the foundation model dialogue and the self-thinking, self-reflection definitely has the potential to further improve the intelligence of the foundation model or the agent.
Thanks. I think that's an interesting viewpoint. So, yeah. Okay. So there are so many the development of MLM and the development is so fast. So everybody focus on how to develop a more stronger and more capable MLM. But there's one point that we may miss, that how to better evaluate the MLMs. So that's also the key points, right? So so professors, what do you think the best way to evaluate the MLM? So this is also the equal question on the other side. What do you think is the real path to AGI in terms of the evaluation? I think.
Yeah, I think this question is especially fine-tuned for me. Yeah. So I just have a keynote talk in the next door workshop called the first workshop on evaluation of generative foundation models. So I think if you want to know the details, you can watch the video playback. But here I want to summarize that existing benchmarks for evaluating multimodal LLMs, that they only focus on enlarging the size of the tasks, right? Like the MMT benchmark, or many more benchmarks you have ever heard in this 2 days workshops, right? And but I don't think that's very inspiring, because the reason why we need a big, large LLM is not to perform as many tasks as possible. Besides, we want each task can surpass their corresponding specialists, and that's a key motivation. So we proposed L1 to L5 benchmarks. You can Google pass to generalist. So the 2 is number 2. So pass to generalist, and you can go there and see that we focus on the synergy across the tasks and across the comprehension and generations. So we coined the level 5 is that there will be the synergy between comprehension tasks like what the GPT-4b excels in, and generation tasks like what DALL-E, Sora excelled, and the regional language processing tasks. So in the future, we call a multimodal LLM a superpower if it can achieve a very high score at this level 5, meaning total synergy. So synergy means 1 + 1 larger than 2. Yes. So maybe in the future, if you can draw a better picture, it means you can speak well. Yeah. So I think that's how we human beings, right? We train our keys to see many visual pictures and to help, and these visual pictures seeing can help the keys to develop better language abilities. So that's our human brains achieve synergy. Yeah. Thanks.
Thank you. That sounds very interesting.
Yeah,
Okay.
I think Haiwan mentioned 2 questions. Yeah. So one question is how to measure the level of the human level intelligence or the generalist. Yeah. Another part actually is, for example, for each level, you need to do this kind of evaluation, how to exactly evaluate. I think the evaluation includes 2 types of ways. So one way is subjective, another way is objective. Yeah. So objective is very fast. Yeah, because no human is required to participate in the evaluation process. But the subjective is better. Yeah. So personally, I think maybe for multimodalities, this kind of foundation model, the best way to evaluate is still apple-to-apple evaluation. So means, for example, you have 2 systems. And this is also a common way. It's a better the better area. So it means it's like for the same question, and you interact with the two systems, and then based on the final result, you will give the score, give the evaluation which system is better. I think maybe in future this kind of evaluation should be better, more flexible. Yeah.
Okay, that sounds very interesting. That's very insightful. Thanks.
Yeah, so to share next.
So, I think there's one core question. Yeah, I would like to raise. Yeah. So, what directions do we need to, or do we want to explore in the future? So, yeah. Yuan Yao, do you have any opinion?
Sorry, what path do we want to explore in the future?
Yeah, I mean, what are the promising future directions that we want to explore in the coming future? Something.
Yes. I think the recent progress of multimodal large language model, we during this process we extend the capability of language intelligence to different modalities, including perception and generation. And maybe this extension will also include embodiment and also to physical sensors in the future. And that's not only extending our application scenarios, that's also a promising way to learn new knowledge from the real world. And also we can make these models to serve as a human level robot. So I think that's a very promising way. But a big problem will be the data. So currently we can easily collect the language data from the internet. And that's also true for vision and other modalities. But for the embodied sensors like a motor and other radio radar sense data, so that's not very easily collected currently. So that will be a big problem.
Okay, thank you. Yeah.
Okay, thank you.
Thank you.
Okay, thank you. So maybe Prof. Han Wang want to share something about the evaluation.
Yeah, that's what I shared in the next door workshop. So I think most of us are in the panel. So it's a co-work by like Fei Hao and some of my students and some of the interns from DJU and Prof. Shui Cheng and me. So it's about a new paradigm to evaluate multimodal LLMs, and we address the overlooked synergy evaluations. So as you can see that to grade this, we have 5 levels. The first one is non-word specialist, which is level 1, meaning there's no multimodal, no multitasks. And level 2 means we want to unify comprehension like image captioning, many to one tasks, meaning from image to language tasks, and generation tasks. Generation means you have detailed instructions and to generate a specific image. And level 3 is that we not only perform to unify them, but we want to have synergy within the comprehension tasks and generation tasks. And level 4 is we want the synergies across comprehension C and G tasks. And this is very challenging because you know that the comprehension is many-to-one mapping, and the generation is one-to-one mapping. So you have to make the LLM to fine-tune the LLM as intelligent as to know when and where to drop, to discard visual features, and sometimes to preserve them. So that's a conflicting objectives. So it's very hard to achieve this harmony. And then level 5 is to achieve the total synergy between C, G, and L. L is a NLP text. That's because if you have ever trained MLMs, you will find that your fine-tuned LLM will be degenerated with its language abilities, right? So you fine-tune Llama 2 7B, then it can never achieve the original NLP text performance. Yes. So this is even harder. So we evaluated this with many existing like commercial or non-commercial models, and we mapped them into this 5-level hierarchy. Yeah. So, and you're welcome to contribute with this specialist bank. And our scoring is based on this bank. Okay? Okay. That's it.
Thanks. Yeah. So if everyone feel more interested about it, maybe you can ask any question after this discussion. Yeah. Does anybody else has further questions from the audience, like both inside or online?
Okay, so
think we
can come here. A friend wants to ask a question, so I ask.
We don't need to do that. Okay. Hi, I'd like to first thank the organizer and thanks Professor Zhang and Professor Yan. I'm a student from NUS and I'm a member of Learning Innovation Lab led by Professor Xinchao Wang. I would like to call back an early question as about the AGI, the future AGI. And I think Professor Zhang mentioned a very important prerequisite, that is if we really believe in autoregressive, if we really believe in this strategy, then everything is only about tokenization and then do the next token prediction. So how can we test whether the autoregressive is the ultimate strategy for AGI? Can we do such kind of examination to make sure we are working on a right path? Yes.
All right. Indeed, I have some theoretical conjectures about that. I grade where I put the definition of intelligence. Of course, it's very hard to define what intelligence is, but I turned this into a 3-level of reasoning. Like the first one is induction, deduction, abduction. So I somehow can prove that, but without any peer review paper, that I somehow can prove that the next token can achieve the highest level of reasoning, which is abduction. And abduction is the key feature for counterfactual reasoning. And if we use the theory of Julia-Prowse causal ladders, so the counterfactual is the highest level. Yeah, so it can make the agent imaginations to imagine someone that never exists before. So I think if this can be achieved, then the real intelligence can be achieved, and that's next token can do. Yeah. So though it's not proof, but I believe this. Yeah.
Yeah. May I have a follow-up question?
Yeah, sure.
Sure. Yeah. As just mentioned by Professor Zhang, we do the next token prediction actually based on the maximizing the probability. So it's maximizing the likelihood. But as Julie said, when we do causal inference, actually we are looking for the causal relationships. It is not just the correlation and the maximizing the probability. So would you mind sharing some details about your logic or your proof? How do you connect it?
If you have sufficient data, then the data itself is helping you to do interventions. So there will be no hallucinations, no the so-called spurious correlations. Yes. And even though there's still bias, and the bias is called common sense.
Thank you very much. Thanks.
Thanks.
Okay, so do we have any other questions? I think it's near to the end. Okay, so
Yeah.
uh,
Thank you.
okay,
Thank you. So if we do not have any other questions, so let's end now.
Okay.
Mhm.
Thank you, everybody. Thanks, especially thanks for the proof 水车岩 and the proof 海王章. Yeah.
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 And thank you, the professor.
Thank you for the whole day workshop. It's a whole day workshop.
Half day workshop.
Half day, okay.
Okay.
Hard working. Thanks.
Okay.
everybody.
Thanks, everyone.
Okay,
Yeah.
thank you.
Bye-bye.
Enjoy
Bye-bye.
the
Thank you,
dinner.
everyone.
Yeah.
Bye-bye.
Bye.
So
Yeah.
let
Yeah.
Bye.
Bye.
Bye-bye.
Bye.
Bye-bye.
Okay. Let me end the meeting.
Okay. Have a good day at
Good
Seattle.
day. A good night.
Okay.
Yeah.
Be good. Yeah.